one of the great alumni of this great old department. He has completed his PhD from IIT Kanpur under the supervision of Professor Parimal K. Bharadwaj. Then he joined Professor Susumu Kitagawa's group in Kyoto, Japan as a postdoctoral fellow with two prestigious fellowships, JSPS and CREST Postdoctoral Research Fellowship. Later, he joined IISA Pune as an assistant professor in 2009 and became professor in 2020. His research is mainly focused on the development and functional studies of metal organic frameworks, MOFs, and related advanced microporous materials for chemical industry, energy, and environmental applications. He has received several prestigious awards and fellowships in his career, including INSA Young Scientist Award in 2013, Avra Young Scientist Award in 2017, Alexander von Humboldt Fellowship for Experienced Researchers, Germany in 2018. He is also part of the advisory board of several internationally renowned journals like Chemical Communication and Chem Plus Chem. He is also one of the highly cited researchers from India and received citation award by Clarivate Analytics. Now, I will not make you all wait any further. I request Professor Shuchit Ghosh to continue from here and share his scientific achievements with us.
So, thank you, Dr. Supradeep, and all of the organizing committee members for giving me the opportunity to present research. And of course, this is a special moment for me because this is just over 20 years I passed out from this college, and I have fond memories of this college, which gave me like foundations of my career. So I'll just share my slide. Is it visible?
Yes, sir.
Yes, sir.
Okay, so today I'll introduce one kind of relatively new materials in this talk. So although I can understand here students are like mostly BSc students, first year, second year, third year, so they are not yet exposed to research, but I'll try to keep my talk such a way that it will be like classroom and it will be basic of chemistry. So it will be like they can understand several basic things, and that way I try to keep my talk. Okay, so the title of my talk is The Fascinating World of Metal Organic Frameworks. So from as we name, we can see here, this is like some framework material which is made of metal and organic. Okay, see some background, we can see some this kind of one framework material. So before going to the talk, I'd like to say here that this college, sorry, I don't have any photo in this college. So that's old photos I lost or something, like I could not find any. So I passed out from this college in '99, and it was very special like kind of feeling for me because see, I joined BSc honors there in the first day of my class. It was 27 students, but then when I was writing the final exam, it was only me. I remember Dr. Christian College was writing exam. So that year only I was the only student in third year final exam. So after that, of course, like I could not visit this college. Maybe in future opportunity I'll visit. Of course, I by Bijnupur I visited. I could not visit college, so I have a lot of good memories. Particularly, I remember Dr. Sankar Chattopadhyay. He was my mentor and really helpful. I don't know, I am not in touch with him, but any help, related help, we used to go to his home, and then that was very good help that time. So that this college was my kind of in this chemistry career. It was important milestone kind of this platform. So I always remember, and I have a lot of good memories with this college. So now, okay, I'll come to this porous materials. So we know different kind of materials. Whatever we see around us, all are materials. So now I'll introduce you with some porous materials. So if you see IUPAC definition of different porous materials. The porous materials are it depends on what is the pore size. So porous material, pore size is, let's say this is less than 20 nanometer, 2 nanometer, that is 20 angstrom. Those are called microporous materials. We use a lot of micro, like day-to-day zeolite material. We don't know what in many things we are using. There are zeolites are there. Let's say if you use like any soap or washing powder or something, there are a lot of zeolites are there, and there are many applications because zeolites are in petroleum industry, and there are plenty of applications are there. So we use even day to day. These are some of the materials, but we don't know. So these are the like kind of microporous material. This is the like pore size is the smallest one, and after that, if it is pore size is 2 to 50 nanometer, that is called mesoporous material. This is some of the like silicate materials made of silica. This kind of materials are called mesoporous materials. And if it is anything pore size is more than 50 nanometer, those are called macroporous materials. So some of them are like aerogel kind of materials, and it is applications. You can see here how this is heat resistant. Like it is hitting here, and our mystic is here, but intact. So that means this is a different important applications for those materials. Just to get idea, since you are not maybe students are not eligible to see this kind of size or something, and then to get idea, see here is the one benzene. The size is almost 70 angstrom, and bond length is current bond length is 1.39. And here is the C. This is, can you just I don't know this, but can you move this? It's not moving. Okay, it's moving fine. Okay, so like diameter of a human hair. See, this is 10 lakhs angstrom. Okay, so compared to this one now, you see this is like 20 angstrom. This is 10 lakhs on human hair diameter. This is the some microscope you will see on human hair. This is the diameter, and compared to that one, this is the pore size. So now you can imagine that what is the like microporous material, what is the pore size, and this it has good applications. Like if you see particularly this chemical separation now. See, we have different chemical, like you see benzene kind of molecules, different molecules are there, and how we can separate based on their size. Okay, so to give some idea about this kind of materials, like porous materials. Now, if you see the history of different microporous materials, so zeolites, of course, these are naturally available, but then we need to synthesis depending on our requirements. So synthetic zeolites started in 1948, and that was the first kind of, we can say, by microporous materials. And after that, these zeolites are made of only like silicon, aluminum, and oxygen. And then if we try to make related material, that is aluminum phosphate. So this is started around in 1982, and then different other microporous materials started in the 90s. These kind of materials are there. After that, this material like this metal organic framework, started like more number of studied. Oh, this material came from around this time. Okay, this is around 90s. Okay, and then after that, many sister materials, of course, field synthesized. This is like organic zeolites related to the sister materials. That's why names are similar, like SOF soft materials, HOP materials, and COF, and different POF materials. These are different materials, sister materials of MOF. So my interest is in this zone, this MOF, and then other sister materials. So now if you see in comparison, like synthetic zeolites are almost now, this is 70 years. So total synthetic zeolites are known around 200. Okay, because here we have only like aluminum, silicon, and oxygen. Okay, these three we can vary, so we cannot vary much. That's why number you cannot see this is more number of the synthetic zeolites. But if you see MOF, now this is around like 2 or 3 decades, more than 70,000. It is much more now. Because here, as you can see, this is, since it's made of metal and organic, so there is almost no limit. Like you can use all metals from periodic table, and organic ligands almost whatever you can imagine. Okay, so like that, that's why there is infinite number you can make this kind of molecule. So then, in simple term, what is metal organic framework, or also known as porous coordination polymer? Okay, so both it is porous coordination polymer and metal organic framework, both are same. Only names are different. So this is more famous, like metal framework name is much more popular. Okay, so all of you in BSc first year itself, you must have learned this structure of basic zinc acetate. Okay, so this is the basic zinc acetate structure. Basically, zinc acetate, you know, like it doesn't exist as a zinc and 2 acetate, even oxygen state 2, although, but he exists as a like this. Okay, in solid state, zinc acetate exists like this. So 4 zinc, the central one oxygen, and these acetate units. Okay, the zinc acetate here. So what will happen, this zinc acetate unit, if we connect by some organic moiety, Like let's say we have infinite number of zinc acetate. If you just connect each of them, this is the methyl one. This is methyl one, methyl one. So between the two methyl, if you put some organic moiety, what will happen? Because if you can connect all direction, like if you go to polymeric structure, it will give polymeric structure. So now see here. See if you connect each one of the unit with on benzene, just only replace methyl by connecting with benzene. So how do you get this kind of 3D material? Because it is extending all direction. Like this is 3D. You can see this is methyl one. So this is basically all direction extending. This you get 3D structure. So this is, if we see from on axis, you get this kind of porous material now. Okay, and now if you have benzene, this you can change with this different, like benzene, different functional moiety you can include, or you can change the length more than one benzene, like that way you can change this. So you can get different kind of porous material. So this is the like simple way to explain what is this like MOF material. Now different kind of MOF materials related, like if it is infinite, that is MOF, but if it discrete unit, let's say here, now we know also copper acetate. Copper acetate exists like this. It is a 4 acetate units and 2 copper, and there are 2 water molecules. They are all like typically water. So this is copper acetate unit. See, copper acetate unit, if this is this kind of 1,3 benzene dicarboxylic acid, it gives this kind of football kind of structure. Okay, this is known as metal organic polyhedra. Okay, these are like porous material, football kind of this shape, and then you get another kind of porous material. These are sister material of MOF, we can see. See now again microporous material, if we see this hydrogen bonded organic framework. So how we can get simple, if we take one this kind of moiety, if you see this it forms this kind of hydrogen bonding, strong hydrogen bonding. Okay, so these are very quite strong. So now it is possible to design, if you all 3 directions, if you design like that, it will extend this hydrogen bonding all directions. So simple, this molecule when you crystallize, you get this kind of porous material. So this porous material in solid, like whatever gas molecules are there inside, we can remove, and this exists as a like simple organic compound. It can give one like porous material. See, this is like how it shows that inside gas molecule can go inside, and these are I'm not going to the detail of this one because probably for basic students this will be difficult to understand, but you can this is a measurement where you can measure the port diameter. So port diameter is around 10 and strong like that. So this is just can get some idea from here. So other related materials we can get. So like this is the COF material. COF material is covalent organic framework. That means like framework material, again like MOF kind of framework material, but this is covalently bounded. So there is no metal here. So there is covalently bounded like one unit to other unit. So that is COF material. This is example of some COF material. See, this is important, like you get introduced, maybe now it is difficult to understand because only one compound, and then first time probably many of you are looking this kind of structure. But see, these things is, I remember when first time, like when during my master time, master in BHU, when someone gave talk, and these things like it really excited me, and then it gives you like some glimpse about the research. So just although you don't understand completely, but I think for students to just get introduced this kind of like research things is very important. So that really helped me, at least at that time. So like this is covalent organic framework material. So this is porous organic polymer. So this is also similar. You can see this structure similar. This is also like covalently bounded this organic framework material. But this is crystalline, and this is either semi-crystalline or amorphous. So those are called porous organic material. So what is the difference? Like you can understand this. Let's say crystalline and semi-crystalline. You know very well. Some of the metal salts you see. This is like crystalline materials. Okay, and if you see like glass and this kind of compound, those are amorphous material. Okay, so those are like, that is the difference of between these two material, crystalline, and if it is either semi-crystalline or amorphous. Then similarly, sometimes simple organic compound, this kind of compound without any strong like kind of hydrogen bonding or like or any other interaction, it can give you also in a like porous material. So these are weak interaction, but still we can get porous material. So this compound when just crystallize here, we get the like porous structure. And sometimes this kind of discrete organic moiety also, it is porous structure. So these are the porous organic molecule. Okay. So now we'll see like why MOF compounds are so unique. Like MOF materials are why so unique here. See, like what is the advantage of this MOF materials? If you see inorganic materials, so like zeolite materials, their surface area is around 1,000 meters square per gram. I'll come to what is surface area. Surface area means whatever is the basically like you can now think about like porosity. Okay, like porosity. Next slide also I'll introduce what is the surface area here. So this porous, if you see the surface area, bit surface area of this one, known material is around 1000. If you see carbon, porous carbon is around 3000. Let's say this is, but this is a non-uniform structure. So this is non-uniform, or this is uniform structure. This is uniform structure, so we can make crystalline material, but this is non-crystalline and non-uniform structure here. So here we get bit surface area. If you see compare, this is more than 7000 meters square per gram. These more materials are uniform structure. We can, this is designable and also flexible. Flexible means here you can see, let's say if you see biological molecule, these are like soft, quite soft, so these are quite flexible here. But if you see zeolite, these are very rigid and regular structure. Okay, but with this more material we can get softness and regularity both. These are like you can get some kind of balance between. We can make also rigid compound, and we can make soft, and you can make same compound, both rigidity and softness we can make. So softness like biomolecules, and rigidity like zeolites that we can get. Now surface area, if you see like how to get more surface area, so just here the simple one from our classic paper I'm putting here. See like this cube, what is surface area? If you calculate, you get like 24 centimeters square. But same cube, if we just make pieces here, okay, several pieces, then we get surface area 48 centimeters square. So if you just each one you will collect, so that way you can increase the surface area of material. So here is the one like different way to increase the surface area. It's a dense solid particle. Now if you reduce the like reduction of size, you can get surface area like here increase. Okay, same one we can make porosity, we can increase, so we can get a lot of like in the surface of this nanomaterial. And this material, if you make a lot of hole, okay, so this is we get a porous solid particle. That way we can get more surface. So why surface is important? Because now if you want to do any chemical reaction, so chemical reaction, if it is only one cube surface, it will react only outside, it cannot go inside. But if it is porous, then molecules can go inside and it can interact. So that way, that's why like porous materials are important. So the simple difference is here. Let's say one brick that is like high bulk density, low pore surface solid. Okay, so like if you see only just this way, like is a, but of course brick, this is not so solid. Also this porosity is there, as you can see. Like if we dip in water, water can go, but visibly you can see a lot of porosity here. Okay, sponge like low bulk density, high pore surface. So what you get? More surface area, more reaction or interaction sites, so more efficiency of the material. So in terms of materials, like because molecules are so small, so if you make a material, it can go inside and then interact. So you can like improve the efficiency. So here is the way to like this MOF material. If you take like, why this is unique? See, if you take 1 gram of this MOF compound, and if you see the total surface area, that surface area, if you add total surface area of 1 gram of compound, is equivalent to 1 football stadium. If it is difficult to like imagine, let's say if you just total what is the surface area of the brick, because the compound is completely porous inside, all surface if we add, so you get like 7,000 meters square per gram. When it is not much more is available. So 1 gram only compound, the total surface is equivalent to 1 football stadium. So that much surface sites are there to interact with other molecules for the like reaction. So that's why porous materials are like important here, because we can like get the more efficiency in terms of like reaction or interaction, whatever it needs. So now if you see applications of these materials, so applications of this material starting from like, if you see here almost water capture, proton protection, sensor, like luminescent material, drug carrier, photocatalysis, gas storage, separation. So almost now this, since these materials we can design like almost whatever way we want. So like if we imagine about any application of any material, so almost all materials you can, this material we can design a similar way. Okay, and we can get those applications almost like this expanding, and we can tune these properties of this material to get any new properties. But then if it is so like so much we can do, then why we don't see this material in application like in every field? So there is one catch here. See, any material need to, like if you see, there have to several like properties, or it should match for commercial like kind of for application. we need to, first of all, it should be cost, you have to see. Okay, so cost of this, let's say if you see either porous carbon or zeolites, of course, it's a very cheap material, it's natural, available, and those materials, so that's why one is cheap. Second thing is that the material is to be usable of, let's say, in industry, let's say one 10,000 cycle or something. So seeing these MOF materials, of course, now there are many stable compounds are there, but these are not so stable like zeolites. Okay, so because these are, you can see, imagine that this is like coordination bond between metal and organic ligand. So this is main problem is that this, if you increase water, this also water as behaves as a ligand, it after a long time it can hydrolyze. Now, of course, there are a lot of MOFs are there which are chemically stable, like in water, acid base, but then it will come to cost. Okay, we have to compete with cost of the zeolites, because it's not only your application is not enough what properties is giving, but then you have to see whether we can and compete with the other materials. But probably, like if you try some unique application, if you get, and then like we can get like any materials, if you from beginning, then we develop, and then we find some of the materials where we can match with, or we can get some properties where those properties we cannot get, although this is expensive, but still we can use. So for that, of course, industry immediately jumped on these molecules and then this kind of materials, and then started to synthesis. So if you like, probably even I also didn't know this BASF, one chemical company. See, this is the world largest chemical company, but we see, don't see in the chemistry lab BASF any direct product, but most of the products coming from like many of them are actually from BASF. So this is a BASF is the Germany-based one chemical company. They started to synthesize these materials industrial scale from 2010. So they are working on this material to find some application which, like industrially, they can use it, like considering cost and then all of their application in terms of stability on this material, and then basically several criteria are there in industry. So they are trying. And if you see here, like one of the application, which is the like just as a simple way to show here, let's say carbon capture and storage. Now, you know, like worldwide, there is a lot of buzz about this environmental application of this carbon capture and this thing. So, like, you know, there's a lot of carbon we are releasing. So these things, there is what is now currently being used, different technology, those are not so effective, and we need kind of materials or something which can more efficiently capture. So here is one example, like if you at certain pressure, let's say it is 35 times of atmospheric pressure, if you fill one cylinder, okay, that much carbon dioxide fill. If you fill this material with some MOF material, so you can, this 9 times of CO2 we can fill on that materials. So this is the efficiency, because here gas molecules can go and interact with this MOF material. Okay, so it can go into the pore and then store, because of strong interaction, we can store so much CO2 gas. Okay, so imagine like if you can future this kind of some material where you can release, before releasing CO2 a lot of gas, so you can store it, and then that CO2 we can convert it to other chemicals. So that will be really useful. Okay, that's what we are trying. So use of this kind of material in industry and also in research. So now we see these are some of the startups. Startups is a new company, they are trying with small material here. So these are the around, like you see now at least dozen of like startup companies are there. They are trying to get applications of these MOF materials. Okay, these are like many professors from different world top universities. They started different company, or even like professional like industry people also they started. These are different, like this is from MOB, and this is the like you can see this is MOB work, this is from Australia. So these are different like company they are starting based on MOB materials. Okay, they are trying to find some applications of these materials. So what is the historical perspective of MOBs? So what is the history of these materials? Okay, so when for the first time this coordination polymer and this MOF, this term used in the literature. So coordination polymer, if you see, if you just now we started to look back to literature, when this term like appeared in literature. So it is way back 1916. Some here Japanese journal, or that time I don't know is regular journal, or some here scientific document, they found that in 1916 it was first introduced coordination polymer, and the next it came in 1964. Okay, this is coordination polymer, this term. And this MOF, metal organic framework, this is relatively new term. This came only in 1995. Okay, so this is the history of this name of these compounds. But if you see some of the early examples, so this early example one is 1959. This is diamond-like open framework. This kind of this unit, okay, this is only connected by copper. This kind of open framework material, this structure is reported in 1959. And if you see, this is like Prussian blue. So this is the structure of Prussian blue that in journal was published in 1977. But see, Prussian blue as a synthetic pigment, commonly known as Prussian blue, has been in use since early 1700. Okay, so like Prussian blue, people are without knowing that using several hundred years, but then only crystal structure like came to know in 1977. So without knowing also some of the this coordination polymers were using for a long time. Actually, they began to expand this field like around 90s. So Professor Robson is one of them who made like at the initial stage a lot of this kind of like materials, open flow materials. And then if you see what is important of this materials is porosity. So porosity is the center of attraction in MOFs. Okay, so who reported first the porosity in PCP, porous coordination polymer, or MOF? So that is important. So in literature, you see a lot of like debate about this kind of material, like who introduced first this application or this one. So if you see, like in this literature, so first porous material porosity was measured in 1997 by Professor Kitagawa here. It is this paper, and then almost same time 98, this was measured by Professor Yagi. So this was measured at high pressure. This is atmospheric pressure up to 35 atmospheric pressure, but this is a low pressure. Okay, this is like surface area because surface area measured at low pressure. And then if it's the progress of the field, see this is the progress of the field. This is how the compound or this kind of material starting to come. So this is the like number of this year, and this is the number of publications of this material. So this is like you see up to almost like 2008 or something. How this is increasing this number of publications in these materials. Now these are the like several of course these are written like in very small fonts, and then no need to think about that one, but these are the I just putting here some of the like milestones in this material. Okay, so like when first time this gas uptake was measured on this material, porosity basically porosity was measured. This is 97. Okay, first these are the some of the record breaking surface area got in 99. Okay, like now it has got like breathing MOF. Some of the flexible MOF was introduced in 2002, and then exceptional chemical stability that was introduced in 2008. So how the field is progressed. So this is the like those are many of you go to research in the future. So you should know like how the one field like start to grow and then how develop. Okay, so like at the beginning that time it was very simple compound like we start to make, and then how slowly this field like start to grow, and then we interesting properties we get, we enter into the like complexity, and this is the large scale synthesis started to make, and then now we are making like people are making MOF based glasses and everything, like different applications we are entering once you know the properties of this one new material. Okay, so now these are the new materials of course is there. Then we have to see like in IUPAC what you know like organic compounds, these all the nomenclature you get from IUPAC, right? So now these are the new materials, so you need to get the nomenclature, the definition you need to get. So recently there is a committee, and then they got the they came up with some definition of this material. Okay, in 2013, definition of coordination polymer came a coordination compound with repeating coordination entities extending in 1, 2, or 3 dimensions. That is the definition of coordination polymer. So that is more general. That means if it is either like any polymeric compound made of coordination bond, either it is one dimensional, it is like chain kind of structure, or sheet kind of structure 2D, or this 3D structure, those are coordination polymers. So this one came in this journal, Pure and Applied Chemistry, 2013 here. Now if you see coordination network, a coordination compound extending through repeating coordination entities in one dimension, but with cross links between 2 or 3 individual chains, loops, or spirolines, or a coordination compound extending through repeating coordination entities in 2 or 3 dimensions. So this is definition much more complex, but see now there are so many compounds, different kind of compounds to put together, to put in one definition. That's how to divide. This is like as a coordination network then, because you have to separate MOF from definition of MOF to come up with different coordination polymer. So now this is much more simpler way to say if MOF abbreviated like metal organic framework, abbreviated to MOF, is coordination network with organic ligands containing potential void. That means all in literature now we see first 1 or 2 decades literature now, like based on this definition, many compounds are written as MOF, but those are wrong now. Okay, but that time it was fine because there was no definition. So that means we cannot call any compound MOF. Okay, any coordination polymer compound we cannot say MOF if it is either 1D chain or 2D. So that means it should have some potential void, not necessarily that porosity should be like it should take gas or something. Even if it is not taking, let's say, nitrogen gas to measure surface area, but it has some potential void, looks like it has some void. That compound we can say only MOF. So that is the like different from coordination polymer. So this is like more broad, and this is the like one only subclass of compound which has potential void. Now I'm coming to our research. Okay, I'll just only keeping some of the like simple term I'll try to tell you, because I know this is not easy to understand for particularly basic students. So based on application of something, I'll tell very simple way so that you get some idea what is the material, what is the potential use, what do in research, what do you do in research, and this kind of thing. So we are working on different advanced microporous materials. So why are putting like in advanced microporous materials in just to put different kind of compound in one platform. Okay. See, this is like metal organic framework, one example here. Similarly, metal organic polyhedra. So this is like again football kind of structure. And this is one field we are working on MOF based composite material. That means now inside MOF there is porosity is there. We can put different kind of material inside that one. So we can making basically mixture of like two material. We can get properties from both. Okay, so take advantage of MOF and then any compound we put inside that is called composite material. Okay, so and then these three are first three are like these are hybrid, like both organic and inorganic, and second two are now this is only organic based. So this is a hydrogen bonded organic framework. See, this is, if you see only this part, when you just crystallize these two compounds, these two salt, basically, this is cationic and anionic, okay, these two. Just if you crystallize these two together in water, simple water, it form a porous material. Okay, so but you need to know how you design, this form a very kind of hydrogen bonded seed, 2D seed, very strong seed. So that's why if you just crystallize simply two, you get a very nice, it called like hop structure, the hydrogen bonded organic framework structure you can get. Similarly, porous organic polymer, we can, as you can see, this is like made here, we can put an ionic compound, ionic porous organic polymer example. So we just like connected here two units and it formed like, because the content part, this enhancer there, we get here ionic porous organic polymer. So these are like, just to give you idea about different kind of porous materials that were working. So now in terms of application, so in terms of application of these materials, we are working on different field. So let's say we are working on separation of hydrocarbons. So why this is important? This is very important. You know, this reliance, let's say they are, what we get all those petroleum products. Okay, so we don't get all this diesel, petrol, kerosene. So these are, we don't get directly like separate diesel, separate petrol, kerosene, all those things, right? So after once we get, then we need to separate it, we need to crack it, we get like a lot of these hydrocarbons. So those cracking things are done mostly by catalysis using these zeolites, and also we need to separate it. So one example is, let's say if you get all those these water bottles, okay, water bottles made of PET bottles, all those plastic water bottles, these are all made from paraxylene, okay, but you don't get paraxylene separately. Paraxylene, it comes with ortho and meta together, okay, and those compounds boiling point difference is only 1 degree, okay, so it's not easy to separate, only 1 degree boiling point. So like you need very long industry still they're using like kind of distillation method. So it's very expensive method that you need to separate it. Okay, so but PET bottles we can make only from paraxylene. We need to separate those two. So now to separate this kind of microporous material it can help. So it can very selectively, because of the size difference, we can separate this kind of hydrocarbon. Similarly, whatever you see like all chemicals, okay, whatever chemicals like many chemicals is, you know, starting point is sometimes only ethylene or acetylene. Okay, but you know, sometimes like ethylene, we don't get, again, we get mixture of ethane or like ethylene. This is like only difference is only few hydrogen. Okay, acetylene, it comes with like CO2. Their structure is very similar. So we need to industry. These are very important to separate those hydrocarbon, because this is the starting of most of the chemicals, all polymeric material. Any polymeric material, this mostly start from, let's say, ethylene. Okay, so but you need to ethylene from ethane, we need to separate. So those are the important, like, industry is a very challenging, and industry they are spending billions of dollars like for the separating this kind of chemicals. Okay, so like we can like here contribute this kind of materials has good potential to separate this hydrocarbons. So that also one field we are working. Quite light emitting material. Nowadays, see previously used to see a lot of those yellow bulbs. Now we don't see, right? Because of this white light, you see like there you need less power, electricity bill is less. Okay, so now if you can develop different white light emitting materials, okay, particularly like single material based on like white light emitting materials, you can develop. So this kind of materials we can tune and improve this material to get white light. Okay, and then here also you can see now previously one bulb that used to come 100 watt, 100 watt. Now this white light we get only less. So we also get easily benefited, like we get like consumption of electricity is less. Okay, so this kind of material we can develop. So fuel cell membrane. So like fuel cell, of course, we don't see normally we don't see fuel cell application much here, but there is fuel cells has a lot of applications here. And then one material we can develop, one material like called Nepeon, it is being used for last almost 60 years. Okay, so for 60 years there is no alternative material to fuel cell membrane. So hope I am in line, and then it is connected, right? Subhrajit?
Yes, sir.
Yes, yes, sir.
Okay, yeah. So sometime please, because I cannot see here anything. So whether I'm online or not, something.
Sure, sure.
Okay. So this fuel cell membrane like Nepeon is being used for more than 60 years. So none of the material, any other material could replace that Nepeon material. Okay. So now this kind of, like this material last 10 years or something, it's showing some potential that okay, it has like properties like Nepeon, even some of the properties are even better. But of course, still Nepeon is a like gold standard. So, but we need to one day replace those material if you want to reduce their cost, because that is very expensive polymeric compound. Now, this last two topics that today I'll discuss some of the applications, like examples like pollutant capture. See, pollutant captures, there is a worldwide problem, like clean water. Clean water, there is the like that's the basic thing that we need, like say for in this world. So that is the like, and pollution is everywhere. Okay, and because of industry is there, so that pollutant capture, and there is no like kind of very easy solution for that. Chemist, we only pollute, but we have to also find solution also. So pollutant captures, this is a very like important problem. And then chemical sensors. So chemical sensor, a lot of like chemical sensor development. This is also, there is no end. We can develop a lot, a very simple one. You see that we measure just at home, like you want to measure how much sugar you have. That's also based on chemical sensor only. Okay, there is some chemicals are there, and we can based on sensor we measure. So similarly, we can develop many chemical sensor. There is one example of like different based on different properties, chemical sensor development to check either for water or even like different sensitive applications. So it has a lot of applications. If you see water pollutants, so water pollutants, what are the water pollutants? So main inorganic and organic contaminants are waters are heavy metals. All we know that lead, mercury, cadmium, those are of course like contaminate water. And the inorganic acids. If you dump a lot of like industry, a lot of acids or something go to water body, and then of course if its pH is not correct, then again those are like pollutant, and then it will that water is again as not drinkable, or the for ecosystem also not very safe. Now anions, particularly oxoanions, like many metals particularly, they are stable finally in the form of oxoanion. Okay, like one metal, if you just it goes to oxygen state, it can change. Let's say chromium. Chromium, if you like throw chromium in chromium 3, but it will automatically oxidize and it will go to chromium 6, and then as a dichromate, it's stable form. That is a stable form. Similarly, arsenic, selenium, those are stable finally as a oxoanion. Just water, it will automatically oxidize, and highest oxygen state it will go, and it will stabilize. It exists as an oxoanion. So there are many oxoanion pollutants are present. And of course, cyanide, fluoride, those are other anions. Now nuclear waste, now a lot of we are getting this energy. So nuclear energy. So nuclear energy, that is good, but then problem is the nuclear waste. Like any nuclear, their half-life is sometimes like million years or so, but then once you're getting energy nuclear, but what about the nuclear waste? Where it will go? So this permanganate, uranate, this cesium, strontium, there's a lot of nuclear waste of this, like even iodine radioactive. So this Fukushima and those lot of news you heard this one, that those nuclear waste thing, if it goes to water body or something, finally it will come to at tap. We have to drink those like kind of nuclear waste, those chemicals. So those are again like important pollutants here. And then of course like organic pollutants are, we are using a lot of pharmaceutical and personal care products, like antibiotics, using a lot of antibiotics, but many of them we don't use and then just throw in water. So those are like cosmetics, and we are in agriculture using a lot of herbicide, pesticides. And then when you're like transporting oil from one country to other, if you see a lot of like news about oil spillage, right? So oils are going to water. And of course, a lot of dyes are using, so those are highly soluble in water. So these are different, basically, chemical product, chemists we are only making, and then we are only polluting, but then we have to also find solutions. So how to get also clean water after removing this pollutants. So here is some of the, like, if you see like just water pollution, if you write in Google, this is a lot of this kind of like pictures here. So there's no end. Of course, so these are mostly from industry. After regulation, also like many times, like my industry, they throw a lot of like pollutants. And then if you see some of the like UNICEF's, their WHO, their reports, like 2.1 million people globally lack safe water at home in 2015. That is probably official report. Maybe it is much more. So what is the safe drinking water? That itself is important. And if you see like water pollution problem, of course, it is like worldwide, everywhere. It is not only more maybe in, of course, poor countries, but then of course developed countries also. It may look like water clean, but it may not be like, not necessarily looking something clean means not there is no pollution. Okay, so like water pollution problem is like there around the world, but of course there is, if you have more control, and then we can keep it much more like water clean. See, like one example is in like England. This is this 2006 year, 25% of disease came from like wastewater. Okay, so a lot of like disease we get from wastewater, like because water pollution related. So now this material, if we want to find this kind of application of like pollutant as the capture or sensing, first we have to see that we need to use some of the materials like which is must be water stable, because we are trying to find application in water. So we cannot use some material which is not stable in water. And this major problem is these materials are water stable materials. So we have to get some water stable materials. Okay, so that's why we are using most of the like all materials which are water stable only. So you can see here like more than 80% or maybe now 90% compounds are not water stable. So only like 10-20% compounds are water stable. So it is quite difficult to design compound which are water stable. So now we are focusing only on water stable compounds. And if you see, like if you discuss some of the like sensing properties, if you know like luminescence properties of MOF. So for the if you are not got introduced with the luminescence, so like fluorescence and phosphorescence probably read, I don't know, like that time we had in maybe third year or master we had. So phosphorescence, now a lot of like if you commercial material like glow in the night, those are phosphorescence. So similarly, like luminescence is that one, that light is there for long time in the material, luminescence for shorter time. Okay, so some material, luminescent material. So this MOF also we can make luminescent MOF material, but there here is a very complex mechanism, very complex. So like charge transfer, like permanganate, like ligand to metal charge transfer. Similarly in MOF, there are a lot of kind of different charge transfer is possible. Ligand to ligand, ligand to metal, ligand to ligand, metal center, between metal centers. So a lot of is complex. Finally, we get some luminescence property. So we can tune, and based on that one, we can design some sensing application by tuning the luminescence behavior. Okay, so I'll discuss that time during some sensing applications. So before that, I'll see some of the examples of like this sensing and capture here. So these are some initial. I'm not going into the details of this this paper. So this is like initial our first compound on this field. This is like sensing of different anions. So how we can in the MOF we have ionic MOF compound. So this is the primary material, and inside we have nitrate anion. Okay, these anions we can replace with different anions. So perchlorate, this is diisonamide here, azide. We can replace and we can tune the luminescence behavior. So this is, and structure also you can see when you're guest molecule removing structure is dynamic. So that we started, and we can tune their like kind of luminescence properties. Okay, so another example is here. Like I'm not going into the details. Some papers I'll go into the details of this one. Here is one what compound we showed that here different explosive. Now nitro explosive compound, different nitro aromatic compound. You know, like this phimosis. This is, you can see this is like RDX and TNT. This must have heard this one. So, similarly, these are some of the other nitro explosives, particularly like TNP is a, you know, this is known as a picric acid, but you know, that is very explosive. It is very dry. Okay, so this is explosive. In fact, this 10 times more explosive than this TNT. So these are the like we can use for sense this kind of compound or mob-based material we can use. And in fact, this was the like first report of like in solution like sensing of this kind of nitro explosive material. Now I'll show some of the examples of oxygen and pollutant capture, and then some of the sensing. Okay, so oxygen and pollutant capture, why it is important. See now, like chromium. If you see use of chromium, see simply if we are using like in laboratory potassium dichromate, you know very well that dichromate is how soluble it is, what is soluble. So now we are using for the leather tanning, chrome plating, and then dye and pigment. Lot of use are there in chromium in industry. Okay, so now what happens is lot of chromium goes to water body. Okay, now see based on like who limit of detection for chromium in drinking water is very less. This is 0.2 microgram per liter. Okay, and these are like chromium for any oxygen state, it will go and finally go to dichromate. So this is chromium is very carcinogenic. Okay, and if you see all worst pollution problem report of 2010 here, among lead, mercury, chromium is one of them, arsenic. So this is one of them. So chromium is a very toxic pollutant. So I'll recommend all of you to, now this movies are available. Even I think this is available in probably YouTube also. There is one movie based on completely chemistry problem related on Hollywood movie. This is called Erin Brockovich. Okay, if you search in YouTube also, you'll get Erin Brockovich in 2000 American on this biographical movie. This movie is portrayed by Julia Roberts. Okay, so this is based on problem of like dichromate. Because of dichromate problem, pollutant problem, how one vibrant industrial city can become ghost city. Okay, so this was like in 1960, this was an industrial city. This is Hinckley. This is near California. This is that city. They like it is roughly 370 million gallon of chromium was dumped in the groundwater. Okay, now that city became now like ghost city here, and then one lady called Erin Brockovich, she fought, okay, for that people who was there, and then finally recently in 2006, that company, this PG&E, they had to pay $295 million. That means this is $1 million. This is almost like 7. That means you can imagine how much in rupees this one. So this is that much, $295 million they had to pay to around like 1,000 people was there in that region, and then this town declared as a ghost town. So how one pollutant can make one city completely like ghost city, that we can see one. This is a classic example. So this is a very nice movie. I recommend all of you, those are interested in chemistry, of course, like all of you, I guess interested in chemistry, so you should watch this movie. So if you come back to like India here, we don't see, but we have also a lot of problem like that, like several industrial area they had to basically close because of this chromium issue. See here, if you see Central Pollution Control Board, these are some of the list here. These are the like chromium contaminated area in Odisha, Uttar Pradesh, and Tamil Nadu. This is in Howrah. This is chromium and heavy metals contaminated area, Nibra, Howrah, this area. So several areas, but we don't see like many areas, particularly our this leather industry. These are all they're using like chromium, and lot of this chromium when is going to water here. See, this is how water soluble, and this water can go to anywhere, basically river, pond, and then groundwater, and then we are drinking that water. Okay, so this is very carcinogenic chromium, and then without knowing, you like we'll have a lot of health effect. This and recently, as in 2017. See, here is like this is on famous US Michigan Lake here. So US still that company that dumps more like toxic chromium near Lake Michigan. This is also so. See here, it is showing that this industry where the chromium they are throwing this lake, it is 20 miles from that lake. In the groundwater, they could find this chromium. Okay, 11 times higher than the normal chromium level. So these are related to stomach cancer and many things, because this is, as you can understand, chromium 6 is highly oxidizing agent. So our water in our body all are basically organic molecules, right? Mostly organic molecules. So it can oxidize many biological compounds. So and that way, so this chromium is very basically health hazardous. Similarly, if you see this tegnate, this nuclear waste, basically, so you are using a lot of nuclear energy, probably like some of the compound. If you see number one is France, they get 74.8% total electricity produced by France is from nuclear energy. So India is 3.6%. Okay, so rank is 27. But what are the major fissile product we get is tegnate. Okay, this is tegnate from uranium-235. And then long life, half-life is around this many years is a half-life. Okay, so once you use this waste materials, what now currently what is being done, we are putting underground, like several hundred meters underground in the ground, we are putting those waste materials. Okay, but those we cannot put, like today it's okay, 10 years, 20 years, 50 years, but those nuclear waste, it will come back to water body basically. Okay, so like this are it produces finally what happens, this tegnate one is exists as a technetium exists as a tegnate. Again, these chemicals will finally form the tegnate, and this is highly water soluble. So this will come to water body, and this will again groundwater, and from there, now we recently found that Fukushima, in the seawater, what is the problem of this nuclear waste like that? This all nuclear waste, it finally one day it will come to the drinking water. Okay. Now to capture this kind of compound, so now currently there is no magic material or anything which can basically capture this kind of compounds. Whatever you see different water purifier or something, there is no materials. So you are using simply, so in the water purifier you are using. See, we have to use very cheap material, otherwise we cannot afford, right? If you that's why using is charcoal mostly. What they're using, if you see that they're changing the color, that is made of charcoal. So it can capture some of the materials. Okay, it cannot selectively capture very size selective, this kind of oxygen specific or something. So there is no such any magic material or anything which can capture particularly chromate or these things are there. We cannot easily capture many of these pollutants. So if we need to develop some of the materials, finally have to see how we can basically capture this kind of there are different methods of there. We're trying to capture different heavy metals or something, but this, if you develop some material, we can selectively capture this kind of oxygen or something, that will be great, so that we can purify bulk amount of water. So now people are trying to design different material which are very specific to particular kind of one pollutant. So here we try to design some compound which is selective for this kind of oxygen ion. See, now we are making water stable MOF. Water stable, if it is normally not water stable, if you make water stable, if you make any compound make of sulfate and phosphate, okay, so those becomes kind of water stable, because you need to synthesize from water and you get water stable due to the high temperature need, and sulfate materials are typically water stable. Why sulfate based? There's another advantage is that, see, if you the structure of dichromate and permanganate you are using because you cannot use directly tegnate because this is radioactive. Okay, so permanganate is a surrogate anion because very similar structure. You can use tegnate and manganate, or we can use renate also. So there, this, if you see the structure is tetrahedral. This is also two tetrahedral unit. Sulfate is also very tetrahedral, very similar structure sulfate. Okay, so now there is structural similarity. Okay, so that means if you do ion exchange, if you take similar ion, then easy to exchange. So here now, if you want to do the ion exchange, then you need to develop ionic MOF compound. Many ion exchange materials are there. So if you ion exchange MOF compound, we need to make ionic MOF. So here is the one we wrote on review called we gave name of IMOFs. So different design principle we here put together to make ionic MOF compound. One simple one is you take metal salt and neutral ligand, one neutral ligand and one metal salts to get ionic compound. Now if you take sulfate anion, now if you try different compound, if you're lucky, you can get some compound where sulfate anions are free in the channel. So now it has structural similarity as you saw from dichromate and permanganate. So now we can try to exchange with the similar ions with this compound. So if this compound I made is water stable, this is 3D framework, and this rigid crystal because zeolite kind of rigid crystal structure. And if you see closely, look at the structure. So okay, so like for students, this is like what do you do? These structures you can, let us see, probably have not seen like most of you. If you make some material, let's say, and then we can get this kind of structure by different instrument. This is called single crystal, like it's a diffractometer. You need to make single crystal, and from there you collect data, and then by software you can finally get this structure. You can see the structure, and you can exactly see the bond length, angle, everything you can measure. So these are the materials, like we get some materials, and from there we could get the structure. And then we only check this compound simply that when we kept in dichromate and then permanganate solution, we saw that within like 72 hours, this is capturing. Okay. So now how to know that? See, this is the oxidizing agent. We have to be careful whether this MOP is breaking or not. So how to make sure that this MOP is not breaking basically here, and dichromate is not oxidizing MOP? What you can do, if MOP is breaking, then that metal salt must be come to this solution. So we can check by, let's say, different method, that solution whether this metal is there or not. Let's say here used nickel, whether this nickel metal is present in the solution or not. If it is more MOP is collapsing, then nickel should be in the solution. So when you check the solution, this one here, by technical ICP measurement of pH, we found that there is no nickel here. That means MOP is remaining intact, and this compound is capturing. And then different like method, we can check whether all elements are present or not. Here we can see this is the like these are different elements here. So this is like chromate is here around the all compound. This is a mapping like all elements, elemental mapping. We can this is the material, and then all different elements we can check. And this is like powder XRD. This is like kind of powder XRD is like kind of fingerprint of this particular this material. If it is matching, like after exchange, also after doing experiment, also if it is whether same products are remaining or not, that means framework is maintaining. Okay. And then depending on which spectra, something we check what is the capacity, and all those things we measured, and we check that at that time this compound can uptake 166 milligram per gram. So that is the highest amount, like among the highest amount that time when we published this paper. And then we check, because we need to capture in presence of different other anions, whether we can do it from mixture or not. We check in mixture also we can capture. Okay. And then we need to check recyclability, other all different experiments. So I'm not going to much details of those things. Those things we perform here. And then we check similarly whether this, rather than MOF, this is called porous organic polymer. Those are much more stable. Whether we can use this ionic porous organic polymer, we check those ionic porous organic polymer also to capture. And this also you can nicely capture. This compound here is renate instead of permanganate. And interestingly, in this case, we can regenerate even 3 molar HCl, because this is much more stable, covalently bonded. So this compound is much more stable. So we can regenerate easily with 3 molar HCl. Okay. So now we see this is chromate. Similarly, this is selenate. Selenate and arsenate. Arsenic problem is there a lot of in particularly this West Bengal. A lot of area is arsenic prone area, and then you see the world map here. Arsenic poisoning here. It's naturally available actually. So like in drinking water, we get a lot of arsenic in several places. Okay. So, but then removing this arsenic from drinking water is a big challenge. Okay. So there are some methods of there, but those are not, again, those are we need to improve to make it much more like kind of affordable. Similarly, selenate. Selenate is one, even there some radioactive selenites are present, that like this is half-life is many years. So if it is there present in water body, again you need to capture this kind of materials, and who guidelines are there is like less than 10 microgram per liter of these compounds. So
sir, another 5 minutes.
Okay, I'll finish. That's why I'm going in.
Sure.
Yeah, and I'll finish this thing. Only capture what I will present here. So now in this compound, what we showed here, that mechanistic details of this capturing of this arsenate with the anion exchange and the crystal structure. So in this report here, we showed that one compound generally it can capture all kind of oxygen, what kind of compound we design. Okay, so these are some of the reports. So I'm not going into details. Those are interested, you can from my website. Some of the paper you try to read, try to understand. I think maybe for particular basic students it's difficult, but if you just get some idea what is research, something, how you design the compounds here, how you made a hybridized compound, COP and WAP compound we made here, and this compound particularly targeted for this oxygen ion, those kind of details we can get from there. And here you see we collected water from Malda district of Kaliachok and English Bazaar. This is known as arsenic prone area. Okay, so their arsenic when you measure from ICP analysis, their arsenic is 46 ppb and 39 ppb. When we pass through this compound, we could like get it below the whole level of arsenic limit. Okay, we did even in the bar scale also. So that way we can basically like we capture arsenic of this compound, but of course this is not the solution immediately, because again these compounds, if you have to go for cost and other things. Okay, so now since I based on the like here audience, I have to go very slowly, so I will not go into the this some of the selective sensing also examples I gave, but I'm not going there. But like cyanide, mercury, these are some important compound sensing that also like we're doing here, and this kind of compounds like we can use. So I just finally go to this like in summary basically. So what we basically today presented some of the examples of like sensing of these mob-based materials, and I didn't like presently I skipped. This is like we could design some compound which is very selective to only mercury, and we can design some mob compound which is very selective to cyanide. And here is some of the examples where it can capture basically this pollutant of different oxoanions. Okay, since we are working on different environmental applications of mob materials, recently I edited one book, and here from around the world, different places like this is Japan, Ireland, this is USA, and now Europe, all countries, they like well-known professors, they contributed this book, and then this book came in 2019. And yeah, finally, I'd like to acknowledge my group members, of course, those who are already did all hard work and this nice research they did, and then my collaborators and financial support from Different Resources Institute and ACL will be very nice. And then finally, thank you, and all of you welcome to visit our campus here. So I'm very happy to like get some questions if you have.
Yeah, thank you, Professor Ghosh, for this wonderful talk. It was really thought-provoking. He's trying to address some of the key issues which we are facing with using MOBs. And now I will open up this discussion for the further question answers. So yeah, if you have any questions, just raise your hand. Yeah, I will take these questions. I can see Gargi. You can go ahead.
Yes, sir. Thank you.
Yeah.
Sir, very interesting lecture. Sir, I have a question in this regard. Sir, as you mentioned that metal organic frameworks can be used as drug carriers. So my question is, how are these materials taken by a patient? Are these soluble in bloodstream for direct injection or water soluble to be administered orally?
So sorry, can you repeat the question again?
Okay, sir. So my question is, as you mentioned that metal organic frameworks can be used as drug carriers.
Yes.
How are these materials taken by a patient? Are these water soluble in? Are these bloodstream soluble direct injection or water soluble to be administered orally?
No. These are not water soluble. So these are like zeolite kind of compounds. So these are like once you make these compounds are not water soluble, because these are crystalline compound, not water soluble. So we need to make like kind of like zeolite are using or carbon compounds are using. So these are not water soluble.
So this is soluble in bloodstream directly?
No. These are not. So these are like a solid particle. We cannot. These are crystalline compound. Okay, like if you have seen zeolites and this is like a stone kind of like most of the stones are also inorganic materials, right? Like this, these are the kind of like if you grind on stone in material, very similar material.
Okay, sir. Thank you.
Okay, because we see the zeolites are also like some of the stones are like zeolite. So if you grind it, you get the powder. You get similarly this powder kind of material. Okay.
Then
So
how it is used from our body?
Biomedical application for biomedical application. Dipendu here from Isaac Kolkata. I think what she's asking is the solubility issue.
Yeah, that's what saying.
Biomedical applications. I think.
Yeah, this compound has some drug delivery like applications. There are a lot of like reports are there, drug delivery. So these are, but not in soluble form, not in the form of soluble.
Right.
in the solid form. Yes.
Okay, sir. Thank you.
Okay, so the next question is Pranesh Chatra. He is a student from third semester, Ramananda College. Pranesh, you can go ahead.
Thank you, Professor Ghosh. I'm interested to know metal organic framework or covalent framework, which is more useful for gas storage and other porosity-related applications.
See, like like if you see MOF compounds and covalent COP compounds, see this compound has like it's like so there are some similarities there, and otherwise see most of the MOF compounds are microporous. Okay, and COP compound if you see mesoporous. Okay, so if you see the porosity or something, so if you see in terms of like let's say gas separation, so one compound has the COP compound's good advantage that it's very stable because of covalently bonded. Okay, and so but the porosity is much more. But if you want to see separate it, let's say some chemical, if you want to separate as like ethane, you cannot use like much bigger porous structure. You need to use that kind of porosity only, microporous, right? Very even ultra microporous, that is like even less than 10 angstrom, like 5-6 angstrom only. So in that case, more useful. So depending on application. So first, that's why you need to understand the problem, and then what kind of materials you need. Okay, then we can basically choose like what kind of material you should like for the application. You should choose the material. So which one is that depend upon the kind of application you are choosing. Is it clear?
Yes, sir. Thank you.
Okay, so one more question I think we have from Srinjay. Srinjay, also student of Ramananda College, first year. Srinjay, you can go ahead.
Okay, sir. Good morning, sir.
Morning.
Sir, it was an interesting talk.
Thank
In your talk, you said MOFs absorb many type of gases.
you. Right.
So can we capture CO2 directly from air?
Yes, now people are also capturing directly from air, like direct from air different method capturing. Yeah, recently started research on this one. Directly air like CO2 capture from air.
Okay, sir. Thank you, sir.
Is there any more questions? If not, let's thank Professor Ghosh.
Hello,
again,
hello. Excuse me.
Yes, please.
Hello.
Mr. Yes,
Yeah.
please. We can hear you.
Yes, please tell me a little bit about the hydrogen storage material which is used in fuel cars.
Fuel cars, yeah. So of course, like similar to like any other gas, this MOFs also like a lot of researchers going on for hydrogen storage. So a lot of hydrogen it can store. Even what is the targeted, like what American like Department of Energy, they said that okay, this much if you can store, let's say using this material which you can use or something. Even by hydrogen storage using MOF material, there is if you check like one car was like they used one Renault car from one continent to another using this hydrogen as a fuel in MOF. But again, those are in research stage because this can do, but again, for it's not in the commercial stage. It has potential, but then you have to see again cost and many other things. These materials, that material like long-term stability, those need to see. So it has potential. Even if you can see, just you can search like hydrogen fuel based on MOF materials. There are some cars you can see video, and then they're running from even like it will like pass through several countries. I think maybe it's not the like one. I think basic component itself, but there's no use as of now yet in the research stage.
Okay, thank you. So it is on research stage.
Yes, it is research stage. Yes, not this kind of like hydrogen fuel in this material based, right? But if you see like hydrogen fuel, once I discussed something, the fuel cell. Based on fuel cell, like hydrogen cars are hydrogen cars are there. So like fuel cell based application, there we are also directly using hydrogen, but not as this material. Okay, we are using the hydrogen car. Those are already in commercial. In all some of the cities are there. In Tokyo, in California, now you can get like petrol pump. You can get like gas pump, hydrogen pump is there, and then there are hydrogen cars are already running. If you just check also, like fuel cell car. If you just write in fuel cell car, you can get that some of the cities already fuel cell cars already running. They're using hydrogen as a fuel. So in future, maybe we might see like hydrogen as a fuel for running car in large scale. So those cars are expensive. What I checked from literature, those cars are, let's say in Indian money, more than 40-50 lakhs. Those expensive. So not in the, that's why not more probably much popular.
Yeah, one more question. That would be the last question to Professor Ghosh. It's in the chat box. Is Madhusudan Mandal asked that it's a very nice lecture and informative. One thing he wants to know that what about the thermal stability of the MOFs?
Yeah, so typically MOFs are thermal stable up to like 300 to 500. Okay, 300 around like 300 to 500 degrees centigrade. Some of them like in that range around. Okay, so their thermal stability is not a issue. So like typically most of the materials, let's say organic compounds are thermally stable up to let's say 200. You are using a lot of material. So, but issue is with the like long-term chemical stability maybe, because different harsh condition, that is the like probably like issue, because see like MOF compounds is a coordination bond, so it can be like not all MOF compounds stable in let's say water. Okay, but now there are plenty, several 100 compounds are there, even like more than 1,000 compounds are there. Those are like stable in water and kind of acid base, like different pH range. Okay, but thermal stability is not issue.
Okay, I thank you again, Professor Sujit Ghosh. Then I will go to the next session. I will request Mr. Dr. Rahul to take over from here.
Thank you very much.
Thank you, sir.
Thank you, Shubhradeep. Am I audible?
Yes, you are, Rahul.
Yes. Okay, just a minute. Okay, so we are now progressing to the next session of our webinar, and this includes 2 keynote lectures, and it is my pleasant duty to welcome the first keynote speaker of today's webinar, Professor Dibendu Das, who is currently an associate professor in the Department of Chemical Sciences at ISAR, Kolkata. So he received his MSc degree in organic chemistry from University of Calcutta, and later his PhD in supramolecular chemistry from ISCS Jadavpur, and also did his postdoctoral work at Emory University, Georgia, from 2010 to 2013. And after that, he returned back to India. And from 2013 to 2017, he has worked at INST Mohali and as well as at ISAR Tirupati. And later in 2017, he moved finally to ISAR Kolkata, where he's serving as an associate professor now. He has won several awards and has got several recognitions to his credit. This includes the Swarna Jayanti Fellowship in Chemical Science in 2020, the Indian Peptide Society Young Scientist Award in 2021, and CRSI Young Investigator Award in 2021. He is also a member of the Early Career Advisory Board of ACS Chemical Reviews, and also several other journals like the Material Horizons, and International Advisory Board member of Asian Journal of Organic Chemistry. So, you know, it is very difficult to completely summarize his total achievements in a couple of minutes, but I can say without any doubt that he is one of the emerging researchers who will be a key player in the area of systems chemistry in the recent future. And the title of his talk today is Systems Chemistry, How Complexity Emerges from Chemistry. Therefore, without making any more delay, I invite Professor Das to share with us the exciting science that is exploring with his team at ISAR Kolkata. Thank you.
Thank you, Rahul. Thank you for this kind introduction, and thank you for this invitation. Actually, truly an honor to speak, especially in front of the students. Hearing from Sujit Ghosh, such quality work. So I think it will be really an inspiration for the student, and very nice lineup of speakers. I apologize upfront because I will not be able to stay longer. I told this to Rahul, unfortunately, because I am traveling today. But still, nonetheless, I will try to give you a glimpse of the concepts of systems chemistry. I hope you can see my screen and hear me. I will take it as a yes. So systems chemistry is a young field of chemistry. It's a truly interdisciplinary field. So much so that I will begin with a quote. I will begin with a quote of Schrodinger, one physicist you might know, about life on a chemistry talk. So you can imagine the diversity of systems chemistry. Schrodinger wrote beautifully, living matter evades the decay to equilibrium. So I will come back to that. I will come back to that meaning of how living matter evades the decay to equilibrium in just a couple of minutes. So this is a phylogenetic tree, again a thing taken from maybe a textbook of a biology, but you might be finding it interesting. This basically gives you very tiny text, but on essence it gives you how life originated 3.8 billion years ago, somewhere here. If you see this reverse chronology from today to 3.8 billion years, from today to 3.8 billion years, it expanded to take 3 domains: bacteria, archaea, and eukarya. We are somewhere here, humans not very important, not very significant. What exactly happened here 3.8 billion years ago is something that is very exciting, very, very, philosophical also, right? How life happened. And more importantly, we might not even know also, to be really fair, with all the technologies we might develop, we might not know how life came on Earth. But what must have happened is that small molecules sticking to each other to create structures which were functional and having, for example, information replication that was done by our nucleic acid, the extant nucleic acid, catalysis done by proteins, and also consuming energy. That is also very important. Consuming energy. Living matter consumes energy, right? We all are here in this webinar. Either in a normal day, I would have been in the college actually giving a lecture. These are all processes that use energy. We use energy, we eat breakfast to come get the energy, right? The day we stop taking energy to sustain ourselves, we are not anymore living, right? So that is also a very critical landmark of living to non-living, right? And then there is this guy, apparently non-living, by the way. By the textbook definition is non-living, but now currently stopping the world. The reason I could not go there, and you had to do this wonderful list of speakers and conference, one-day conference online, because of this guy, right? This is, as you know, a virus which can replicate, which can have Darwinian evolution in a way. It can have a ensemble of sequences under selection pressure. Delta plus can come up and again stop the world, and delta, I don't know what, gamma can come up. This cannot make its own protein, by the way. So hence we cannot call it living per se. Anyway, that is complicated. I'm not a biologist also. The reason I'm trying to push it up is that I'm trying to build up is that systems that were in the beginning of Earth were really intelligent, right? Can we create those on the bench? And can we learn a very tantalizing question like, can we create life-like objects, life 2.0? Obviously this looks like science fiction, but we are getting there. We can create systems which can consume energies to create nanostructures, which can replicate, which can have selection pressure. There are many, many check boxes that had been ticked, but still we are far off from creating living matter-like things on the bench, right? So we'll talk about that. I will talk about that in the context of supramolecular chemistry. So what we use very small molecules. You can imagine that, needless to say, and as done by the Miller-Urey reaction, you might have read about it. You can still read about it. The classical reaction shows that very small molecules can generate nucleic acid, amino acids, and also some peptide, dipeptide type have been generated. In fact, that was the first interaction I felt in Georgia Tech in my postdoc, MIT University, very close to Georgia Tech. There, the Miller-Urey samples are still there. They're still doing mass spec to know that, remarkably, that in that setup, if you remember that, most of you might have seen it, but you can Google it also. Miller-Urey reaction in 1953, I think, that was having this lightning simulation under gases that could have been there in the prebiotic world. That created various nitrogen containing small molecules. So we use those maybe very close to heterocycles, which were expected to be there in early life, or rather before life. We use those to create a battery of structures, right? A very advanced enzyme. Maybe I'll talk about one example from that. Nucleic acid. Can we create protonucleic acid? What is proto? Proto means primitive nucleic acid. Can we create by this cocktail of bases or cocktail of small molecules? Can we create something like a short nucleic acid and short peptide collaborate to create something like a ribosome? One of the finest feat of nanotechnology. Ribosome is only 15 nanometer long. We talk about nanotechnology, but nanotechnology is there in all living systems. This is incredible motor, right? It can create information, it can process information from digital to analog to digital, in fact. Anyway, and from there, whether we can create non-equilibrium polymers. Non-equilibrium polymers are the exotic polymers of biology. I will talk mostly about this today. I'll show you some movies so that I can catch the imagination of the young students out there, and how we use very simple chemistry to ask questions based on whether these small molecules can achieve the complexity of life. Okay, that is the premise, and these are all energy driven. As I said, the defining factor, apart from we give too much credit to replication. Sometimes replication is important for life. This metabolism is very important. We have to use molecules to create more beneficial molecule, right? That is how we create energy. That is also not from the context of lighting up a bulb, which I think Professor Ghosh beautifully, talked about. But here in the context of living matter, right? We need energy by consuming food, ATP, right? So those things. Okay. So how is different from supramolecular chemistry? You might think about that. I talked about molecules sticking to each other to create structures. This sounds like supramolecular chemistry. You might have been exposed to that. But supramolecular chemistry last 6 decades has been wonderful, right? We all know, like for example, I'm taking these 2 snapshots from 2 review articles. These are nucleic acid-based supramolecular systems. These are peptide-based supramolecular systems. These are all biology-inspired. These can be forming very stable structures which have tangible lifetime and can be functional, like for drug delivery, for filtration devices, for sensing and whatnot. MOFs, as again Professor Ghosh talked about, molecular crystals, micelles, are all fascinating example of supramolecular chemistry. In fact, Nobel Prizes have been won. 2 Nobel Prizes have been won on this field of supramolecular chemistry and allied field of actually systems chemistry, a very early systems chemistry, I would say. But even examples as we speak on the context of COVID-19, this classical remdesivir drug, you might have heard about it a lot. There was black marketing at some point. So this remdesivir drug is solubilized, would you believe, in a beta cyclodextrin, which is like a cup-like molecule, right? You know that, and that goes in, the drug goes in, solubilizes that. And that was used by Gilead. Gilead is one of the leading drug companies, among others, to solubilize this highly hydrophobic drug. This is remdesivir, and this one. The point I'm making is that supramolecular chemistry has given us some life-inspired structures like these weak forces for various functions. For various functions, supramolecular chemistry has given in the last 6 decades. But if you look at, really ask that whether these synthetic systems are really natural or really mimicking the self-assembly processes of nature. That is the question. So that's where I come back to the quote of Schrodinger, a physicist, about living matter events at equilibrium. And if I draw a very rudimentary diagram of this free energy, if you see the reaction processes, these go downhill, right? These go downhill and stabilize, or maybe in a kinetic trap state, depending on how long big is the barrier. The barrier is larger than kBt. This will be stable for a tangible amount of lifetime. The point is that all these examples of supramolecular chemistry, despite they are mimicking biology and living matter, they are not actually mimicking the processes of living matter. Where, again, this might be technically not correct diagram, but anyway, we'll give it as a concept. Here, in biology, we use energy to polymerize. We use energy to self-assembly. We don't use the energy, downhill energy. We use the energy that is released from molecule breaking down, like an ATP breaking down, again a Nobel Prize winning work, releasing energy. That energy can fuel the self-assembly. That is very profound, right? So it's like a fuel, it's like a chemical fuel. What is a chemical fuel? A chemical fuel is basically, very simple definition, is a thermodynamically activated but kinetically stable molecule. So ATP is pretty stable, but it's very activated. When you break ATP, there's a lot of energy release. That energy can be used to drive a self-assembly process, right? So can we use that energy released from a chemical fuel, like this energy, just like a petrol in a car, or your bike, when it runs out, you stop. You cannot drive the car or ride the bike, right? But you need that fuel there. Just like that, we need ATP to be derived from various sources, right? So that is what we were interested in. Not us, many people before us, obviously. This is very exciting field. And what nature does with this energy? For example, I'll give you two classical quintessential example, and this movie in Nikon microscopy, very classic. Again, you might have seen this movie. This is a 5-wheel cell forming in a matter of 2 minutes in cell division. In a matter of 2 minutes, they're forming. In a matter of 2 minutes, they're dissolving. They're doing a job with remarkable spatio-temporal control. Spatio-temporal means in a sense of space and time, right? They're doing it perfectly whenever it's needed. And when the energies are added, this is done. When the energy is expended, that is dissolved away. These polymers are dissolved away, right? So these exotic polymers is seen across life forms as an evolutionary strategy, and chemical fuels like ATP is the hydrolysis of ATP or GTP, like guanosine triphosphate, adenosine triphosphate, is coupled with this self-assembly process or polymerization process. You can say that these polymers are happening, doing a work like a muscle movement. Like this is even weird, very old video, by the way. This WBC is trying to chase a foreign body. This is also acting polymer dependent, self-assembly dependent. But again, this is driven by energy. This is using ATP, this is using GTP. GTP is being converted to GDP, guanosine diphosphate. One phosphate is releasing, and that energy is doing it. This is only possible when you break the constraints of equilibrium. That's the point I'm making. And if the students, some of you get it, it will be great for me. So these structures are possible when you break the constraints. This remarkable spatio-temporal control is possible only when you break the constraints of equilibrium. These are not stable structures. We are not creating structures. We are stable. These are doing for function, but these are very dynamic. Okay, they have a function they have a function or a role as a function of time, right? As a function of time, something is happening. That is the story we are building on. So to go in detail for the students, what we do, we start with this building block. Let's say what happens in biology. This is a polymer state. These green filaments. Okay, if I don't know, I cannot freeze it anyway. These green filaments is this one, if you can consider like that. And this is a building block, a dimer. In presence of GTP, rapid polymerization happens. Initially, basically, it's downhill. We can follow this laser. It's downhill and then it goes uphill. Why? The hydrolysis of GTP to GDP happens from the self-assembled state, and that results in accessing a non-equilibrium state. This is a non-equilibrium state, remarkably stabilized by the waste product. So we call it now waste product. GDP is waste product. So as you do, petrol, gasoline is the fuel, and the waste product is all this nonsense of carbon monoxide, dioxide, and all. So these are the waste product there. Here the waste product is GDP, which can be recycled, by the way. Biology uses it beautifully. Now that is what is going on. So if you look at critically what happens when you add this GTP to this building block, it polymerizes. In the polymerized state, there is an acceleration of catalytic capability of the polymer. What do I mean? I mean by that, these polymers can break the GTP to GDP only in the polymerized state. So there is something like A mixes to B, they polymerize, then B kicks away A, again come back to equilibrium. This is how the transient non-equilibrium structures are forming in biology. These exotic structures are forming. So the critical point to note here is that there is an acceleration of catalytic potential. This monomer can also break GTP very slowly. But once the GTP and this monomer binds, it's a building block rather than monomer. It's actually a dimer, but for clarity, I'm talking about this as building block. Building block and GTP mixing will form these polymers. These polymers will break the GTP to GTP, then they will crash on. This is the concept. Looks very interesting, and especially the take-home message is that there's an acceleration of catalysis upon self-assembly. That's why the red line comes in. So the growth is controlled on its own. It's a feedback process, right? So you can go as long as your fuel is there, right? You cannot go beyond that. So there's negative feedback. If you drive too fast, fuel will be burning too fast, and that will stop your car, right? We'll go further, but there's a feedback process from the fuel. Here also there's a feedback process in a way where the length of the polymer grows, But after the polymer forms, subsequently the GTP, which is the substrate, breaks, and that comes back to equilibrium. Again you add GTP, again this will keep forming. There is an acceleration of catalysis. If you plot the rate versus time, there will be a spike of activity after some time. There's a spike of rate after some time. Okay, that was the thing that was the genesis of this polymers of biology. So we were not the first, as I said. Back in the day, Vanes group and Ilkema group published a work, a very seminal work in the journal Science magazine, where they have taken this acid, this diacid basically, and they added a sulfate, methylating agent, dimethyl sulfate. The idea was that this acid, now shown like this, only one acid is shown for simplicity. This methylating agent will methylate this acid to form an ester, right? This can be CO2 minus, can be methylated to ester. And this ester will be slowly broken because of the presence of a very nice balance of hydroxide in the background. So what the point is that the hydroxide is slowly breaking the ester, resulting in the disassembly. So first you start with this acid, you just add methylating agent, a tiny amount, very carefully chosen amount of hydroxide in a small vial. And what you see is remarkably the movie, the supporting information movies are really something to see. This is just like biology. The fibrils are, this red fibrils is shown here, are forming and breaking just like the movie I showed you earlier. So here the acid is getting esterified, the esters are polymerizing, the hydroxide in the medium and the background is breaking the ester, and gradually they are crashing out. So this is happening, but if you look at it, this is not a true mimic of what exactly happens in the GTP-driven polymerization of cytoskeleton proteins like microtubule. There, the catalysis was happening from the assembled state or the polymerized state. In this case, the catalysis is happening because of a background hydroxide in the medium. There was something to note. We noted it, that if the hydroxide is there, it's just like kind of like an activation-deactivation rate. If you activate it very fast and deactivate very slow, you can find some population of these fibers, and that's what they are doing. It's a really seminal work. Subsequently, one more paper came out, this time by Prince in Leonard Prince group in Italy. That is also a fascinating work where they have used lipids in presence of ATP to drive the vesicle formation. I think some of you might know vesicles are these spherical structures formed by the self-assembly of surfactants. So when they added ATP, the vesicles were forming, but they had a very small amount of enzyme in the solution that was slowly hydrolyzing ATP to AMP, and that was resulting in, again, transient temporal generation of these vesicles. Okay, these vesicles were generating only as a function of time, but then they were breaking away. So again, a fascinating piece of work, just like showing the mimicking the biologies, the biological system. But again, if you ask at it, this is not hydrolysis from assembled state, right? This is not activation from assembled state. So in fact, Prince came up with a critical review later on. The same author came up in a review later on. So you can have a look at the review if you're interested in theoretical chemistry. They said that this is really top class work, but this has a difference, at least some distinction from the system of biology. I'm giving it again a very cartoonish look of a petrol being there, a gas being there, gasoline being there. They're adding the petrol in biology. This is GTP. This is resulting in polymerization. In polymerized state, the GTP is breaking to GTP and resulting in coming back to building block. In this case, if, for example, the science paper also, again, a seminal work, a top class work, but there they had hydroxide in the medium. So we asked that this is actually not truly mimicking the GTP-driven polymerization, where the self-assembled structure was subsequently breaking the GTP because there was an acceleration of catalysis. There was an increase of catalytic potential or the catalytic activity. So that is a difference we noted, and in fact it was noted by others also. This acceleration of catalysis is not only seen in microtubules, you might wonder, or only in actin-driven polymerization or the muscle movement. The muscle movement is also driven by ATP and NTPs, that nucleoside triphosphates. But this is also shown in other systems of biology. I will not go into detail on that because this is mostly a chemistry audience. So what we thought is that the way out could be acceleration of catalysis from assembly state. That is the way out. It can be used very small molecules to do that. So what the idea is that we take a surfactant or a peptide, very short peptide, we add a ester, maybe not GTP, GTP is too stable, too kinetically stable. We add a pantophenol ester and see what happens. We expected that it will form an assembly structure, polymerized structure. The polymerized structure will be subsequently breaking the ester that was driving the polymer structure. That was the idea. So what happened with Shubhajit, who started this work in IISER Kolkata, that he used a surfactant, again very easy to understand the surfactant, right? This small amplifier with lipid chain and histidine, very easy to make, two-step reaction. We made this and we made it in 20% EMS water. There was no networks. What do I mean by networks? They don't self-assemble per se to form a gel. What is a gel? A gel is just like your hair gel or a capsule gel, if you have seen that. These gels are basically a solvent that is trapped by fibers, networks inside, very tiny fibers, nanostructures there. When you turn down the vial or the container, it will not fall. The water or the solvent will not fall. So when we added this in the solvent, it was not up to 30 millimolar, was not forming any structures. But when we added this molecule, this green ball, spherical ball kind of molecule with pantophenol and EDC, we saw that some structures are forming, a hydrogel is forming, or maybe a DMSO containing hydrogel. Remarkably, after some time it was breaking. So it was very interesting to see that a transient gel was forming. In this case, as you might have noticed already, that there is no other deactivating agent. It is forming because of this ester being there. EDC is, by the way, a high energy coupling agent. EDC is just like DCC in your curriculum. Maybe you have read that. This is a coupling agent for an acid and an amide, or an acid or an alcohol to form an ester. Esters are kinetically stable, thermodynamically activated esters, like an ethyl acetate solvent. Okay, so this is forming. We have used a subset of the concentration, and that is leading to this kind of structures. This is forming like that. This is breaking. We see on electron microscopy structure. The electron microscopy can do really high resolution structures. They're only 500 nanometers scale bar. You can imagine how tiny these fibers are. They're forming these networks. These networks are stable only as a matter of time. After some time, they are becoming solid. We did confocal structures. These are basically solution-based. Microscopy, we saw that these tiny fibers are forming. These fibers are dissolving as a matter of time, right? These are forming and breaking just like biology, biological systems. We have now movies also based on that. We don't have a working confocal in IISER Kolkata. We're getting it very soon from the fellowship. But the point is that we could see that these are also doing the structures mimicking the concepts of biology, especially from the context of activated ester addition, especially from the context of there is no other deactivating agent that has been used in a paper like Leonard Prince Nature Chemistry I showed you, where they used an enzyme, or somebody like Vanish, again a classical paper, they used a hydroxide. In this case, we have done this degradation is going on their own. So what is the reason for that? We did NMR. I will not go again in detail into that. NMR shows that indeed the transient structures are forming and breaking. We did multiple studies. We did refueling studies. What is refueling? When your car runs out of petrol, your bike runs out of petrol, you can add it again, and then again you can start, right? In this tiny vial, we could add EDC again. EDC is the fuel in this case. That was leading to self-assembly structure again. Gels could be again formed, and again it was breaking. We did a pH versus a rate profile. So pH versus rate profile. Rate profile let us to know that this mechanism is happening via cooperative catalysis, where the two histidines are cooperating with each other. One histidine acting like a nucleophile, other histidine acting like a proton source to activate the ester. And hence the assembly, after assembly, when the assembly is happening, if you can see the camera, or it's very tiny, maybe the video is, you can, my fingers will be histidines, and they are breaking the esters because they're very close to each other. And hence we're using hence And I don't know, my mic was, my speaker was turned off. I don't know for some reason. If this is something was being asked, let me know. Okay.
Everything is okay, sir.
Yeah. Okay. Fine. Yeah. So then Pavel subsequently used a similar concept to generalize in a different paper, where he used the same surfactant, but this time rather than using ETC, directly added the ester. He said that, why should I add a ETC? I will add the ester just like biology does. Biology adds GTP to drive the polymerization. He added this FNP. Don't worry about the acronyms. It's basically a kinetically stable ester. When this mixed with the histidine amplifiers, it is forming this self-assembled structure, and these are forming and breaking as a function of time. Okay, so again, basically the same story. We get a transient gel to be formed and being broken with time. The concept is very simple. We add the ester, we add the histidine. They are forming self-assembly after, in a way you can say co-assembly. They're mixing them together to form a structure, and the structure, when they're close to each other, they're subsequently breaking it. Okay, there is a feedback process. There is a negative feedback process. Okay, the title is, in a way, the title of this work is that negative feedback driven self-assembly. Okay, the feedback is there. Once the growth happens too much, we stop, right? Something like that. When we do some mistake, we understand by some feedback was in our body, we stop the mistake, right? That is kind of like this. It's not a mistake, it's doing a structure. Structure is forming and breaking them. Okay, all right. So we did CD and we did the others, mechanical properties understanding. Again, these are too advanced for your curriculum or for maybe your interest right now. But what the point I'm making is that we can see tangible strength of gel. So you can imagine your hair gel one day fall, the next day you find it hair gel to be a gel. So one day it is free flowing, the other day is gel, and the third day it becomes again a free flowing. Something like that is happening, and that has remarkable application in taking a medicine also. You can imagine the medicine you take, the gel structure will be there, not release the drug very fast. Then it becomes a salt, suddenly it will release the drug, and again it will become a gel, again it will stop releasing the drug, right? It will control in a spatio-temporal manner the release of the drug. This is also exciting from that context. So we did TEMs and electron microscopy. I'll skip this part. This shows structures which are there only when the gels are forming. So this part is, yeah. So the point was that once we checked the activity and plotted the rate, we found this smoking gun experiment. In a way, we call it a smoking gun experiment. Why? This is actually a proof that indeed there is an acceleration of catalysis after self-assembly has formed. So again, A and B mix, and when they polymerize, if you see that is a spike in activity, we call that it a burst phase, burst of release of hydrolysis, and then it becomes saturated. The control system doesn't do that. That shows that our system is in a way mimicking beautifully the natural systems of biology. Okay, all right. So this is the concept again driven, given juxtaposed with this actual system of biology. This is the microtubule inert system body which hydrolyzes, and this is conspicuous by its absence. There is no deactivating agent here. Here also in our system there is no deactivating agent, right? This is happening when you add the ester, it polymerizes, the self-assembles, the self-assembled structure gives the feedback and it crashes down. So these are transient structures which are forming and breaking up. All right, okay. So you might ask, why would I be interested in a structure which is breaking on its own, right? Usually I like my hair gel to be stable. I don't want my hair gel to be liquid one day and solid the other day, right? So that is a good point, but there could be other functions also, right? There could be other functions also. For example, this latest paper last year, middle of last year we published, where we showed that these structures actually can conduct electricity as a function of time. So if you have a hydrogel, if you have a solution, usually that is stabilized, right? You take a coffee and how much it's conducting electricity, there will be a finite amount which will not vary with respect to time, and that's how we define equilibrium. We define equilibrium, the textbook definition is that on an average, we look at the system, it doesn't show a change, we take it as an equilibrium, right? But if you look at it, nothing is on equilibrium, it depends on how long you're looking at the system, right? But anyway, if you look at this systems, what happened, this is a very complicated diagram, but you can imagine here the nanostructures are forming at 40 minutes. After a few days or even 3 hours, the structures are degrading. When we measure the conductivity, found that the conductivity is increasing rapidly and decreasing. So how is that important? The important from the contents of secure devices, right? I don't know whether you've seen the movie Mission Impossible, where the protagonist throws away the goggle after the message is read out, because it was mentioning that it's a self-destructive system. After the message is delivered, it will be destructed. In this case, we can have a conductive switch. I will give you the solution, which will be a trade secret. You can add the solution, it forms a gel. That conductivity happens, it opens the gate, and after that, if you don't have the solution, it will not open again, right? So the solution will be the chemical key can be there. A key will be a chemical. Anyway, so that will be one of them. Then we control enzyme activity also in this following paper by these self-assembly structures. We did in this latest paper, we did sensing some small molecule. Obviously, these are not per se relevant in diagnosis and biochemistry in a way, but we showed proof of principle that cascade catalysis, we can show some sensing of small molecules, or we can do some Boolean gate, logic gates we can devise. And as I said, we have done also temporal release of drug, and that is under review still. This paper is under review. We are interested about this finding also. Okay, so I will move. I don't know. I have how much time, Rahul? I think 5 minutes.
Yeah, maybe 5 minutes.
5 minutes. Okay, so I will wrap it up here faster. So other part of the group that we are doing is also systems chemistry. Obviously, what we are doing is that we're trying to mimic enzymes of biology. Okay. So what really happens there? So if you look at enzyme can do a lot of things, right? So for example, any enzyme you can take, you can express, you can buy from the Sigma Aldrich website. These enzymes can do a lot of functions. But if you ask the enzyme that how big you are, they are at least 100 amino acid long. And if the 100 amino acid long amino acid sequence is there, you can imagine nature had to test an astronomical pool of sequences to get the actual sequence, right? So my point is that 100 amino acid permutation combination will be an astronomical number, right? So nature had to test it to find out the proteins of modern or contemporary biology. The point I'm making is that how nature did it, how it was possible. A short peptide was acting like an enzyme. And that's where we came in. We thought that maybe short amyloids or maybe a peptide which can assemble in harsh conditions. So we have some short peptides. I think you all know what is a peptide. It is maybe a few amino acids. We are using only 7 residues or lesser than that. These peptides, amino acid residues, coupled with the amide bond or peptide bond, they self-assemble in very harsh conditions. And then this can show catalysis, and that is the idea we are also pursuing. In this work, what we did initially, we started to mimic an aldolase kind of activity, which was published initially by a computational design paper work where they have used this aldol adduct. You might have been exposed to this kind of chemistry to form this retroaldol reaction. So we did the same with short peptides. Okay, I will not go to detail of the characterization because this will be something that we can look at it. They look pretty, but the concept I'm making is that when we added the peptide, the nanotubes, we found that rapid retroaldol reaction is happening. Okay, we are very happy to note that. Yeah, this is the data with HPLC we also did. So the point is that we could break aldol adduct to an naphthaldehyde and an acetone. Okay, and this is the chromophore. We can measure the absorbance or fluorescence to measure the activity. We did controls without lysine. The lysine is the active site member, and we could show that without lysine it is not working. Yeah, so I will skip this part. I will show you this TOC, and you'll understand that, especially if you're interested in organic chemistry and you're trying to pursue a career in organic chemistry. When we mix all of this together, right, 5 of them together, we find that first of all, this retroaldol happens, and then a forward aldol is also being happened by this short, tiny peptides. So this is really unprecedented in a way. Usually, nature uses advanced retroaldolase and forward aldolases to conduct the metabolism of the CC bond manipulation, right? The CC bond manipulation is very important for metabolism. In this case, we are seeing that a short peptide can do this just the same, where we can see retroaldol and forward aldol and selection also. And finally, I will go to a very, very interesting topic which you might really interest the students out there, which is this covalent catalysis. So what is a covalent catalysis? For example, in the human eye, you have lysines, these primary amines, which can bind to this aldehyde. Forget about the structure, you don't have to worry about the structure. After this addition of this lysine, this forms an imine bond, and then this light dependent signal transduction happens where cis trans happens. You might know, again, this is based on your interest. This results in a signaling cascade. So imine bond is used for a very advanced process of vision, right? Similarly, this is a bit complicated. Here I will give you a very simple example. For example, I want to open this sanitizer bottle, right? What should I do? I should open the sanitizer bottle with my hand like this. If I want to refill the bottle, but this hand is also important, right? To grab this bottle as an anchor. So we are using this hand as an anchor and this hand as a catalyst. Biology does the same. Biology uses lysine, primary amine, as an anchor to the ketone to form an imine bond. Again, you might be knowing this. And then imidazole comes in to pluck away the proton to create the product. Without this lysine, which is apparently not important for catalysis, right? This reaction is not important for lysine. Without this lysine, the reactivity drops down. We tried to mimic with our peptide, where we published this in last year, where we took this peptide, very short peptide, again forming nanotubes, and I will go straight to the mechanism, where we have these blue knobs as lysine, and the histidines are there exposed. Histidines are the catalytic unit, the lysines are this right hand, right? The left hand is the catalytic unit. So when we did that, the activity was very high. When we did a control where the hand was somehow not, or maybe hand was slimmed and not visible, like an arginine, arginine cannot make an imine bond, right? Lysine can. Arginine has a guanidine group, it cannot make an imine bond. Although the pKa's are similar, it cannot form an imine bond, right? In this case, the activity is far lower, which is quite interesting because the active site is the same. Histidine is the same, the activity goes down. So that's where we found out that the lysine was the highest, while the arginine or other controls were not at all good. Okay, all right. So with this, I close this talk and I thank my students. They are actually the worker in the lab. I am the cheerleader sitting here in the AC room. That is also AC, but they are working hard, far more harder than I do. This is the bunch of funding agencies that have supported our lab. If you're interested in the systems chemistry, and Rahul, I think, is one of the young leaders, I would say, very soon, whenever he establishes his lab in this field, he will be also. So we have done this conference last year because these ideas are now crystallizing of systems chemistry. So this conference was done last year. We have done a conference this year also with UCLA, Munich, and other places. IISER Kolkata was involved. And in 2023, IISER Kolkata on its own, our lab, my lab, is doing this conference of systems chemistry. If you are interested, do send an email. Maybe now it's too early, but within maybe 6 months or 1 year, we'll start taking the process of organizing this conference of systems chemistry to discuss the ideas of systems chemistry. Okay, with this, I thank you all.
Thank you, Professor Das, for sharing with us your very interesting research. And now the floor is open for discussion. Any questions? Das. Okay. So, Gargi, go ahead with your question.
Okay, sir. Thank you.
Gargi is an undergraduate student of our department, as mentioned before. So, please go ahead, Gargi.
Thank you, sir. Sir, it was a very interesting talk. Sir, what can be the possible practical application of solutions? Forming gels for some time and again turning into a solution?
Yeah, this is a great question. I think that we are all asking. You all in the field of systems chemistry is asking, and that is where I showed a slide. I thought a smart grad student, undergrad student can ask this. So we are getting some really functional systems which are changing as a function of time. Okay, so we are getting some roles like conductivity is changing as a function of time. That could be useful, right? For security devices, for diagnosis. So we usually do diagnosis in a dead medium, but here we can do a live medium diagnosis. We also did, for example, transient systems to know double marker tests, right? For example, double marker tests are used for various things. Even pregnancy checks, kits are there. The two markers have to be there to be positive. In this case, we have done that. This is only possible when you break the constraints of equilibrium. We are still at early days, Gargi, but we are creating systems which can be using the dynamicity to have a control over functions. Okay, all right.
Yes, sir. Thank you.
Any more questions? Okay. Okay, and the next person, I think Deepriya, please go ahead.
Thank you, sir, for sharing such details about your research. I want to know how we can measure the strength of a gel.
Okay, so that's actually, yeah, that is done via a machine called rheometer. Again, a gift of pieces to chemists and biologists. So rheometer actually measures the strength of, let's say, the storage modulus and loss modulus of a particular gel. So if the storage modulus is higher than the loss modulus, then it is usually termed as a gel. So from those parameters, you can actually specifically tell that what is a strong gel, what is a weak gel, what is a more elastic gel, what is a less elastic gel, you can say that. So you can look at it and search online rheometer of gel. Okay.
Okay. If
Yes,
there are,
thank you.
okay, if there are no more questions, okay, I have one question, Professor Das. So you mentioned about this Boolean logic controlled catalysis and other things, transiently controlled systems. So is there any example in biological systems where we have a transiently operating system? Of course, many things in biology, most of the things in biology operate out of equilibrium. So which is controlled by Boolean logic? Any specific example?
Boolean logic again comes from electronics, right? That logic gates where you have, let's say,
what I mean is, if like in case of a biological circuits or chemical circuits, so we have inputs and some transient output like cell division or like cell mutation or something, and then the feedback. So is there any well-known example in biology like that?
Well, I would say, brother Rahul, every signaling cascade is like that. Every signaling cascade, if you look at it, there is a substrate channeling event happening. There is A to B to C, then A feeding back to C. So if you look at it, they are all complex logic gates, and they could be concatenated like one logic gate over the other. For example, this one we tried to do, if you can see on the screen, A and B we are adding to create this thing, and then this comes in to add it. This is very, very simplistic. We cannot even say that this is mimicking biology in that sense. But biology has many layers of complexity over there. To answer your question, I don't have a specific example in my mind from biology, but there are surely all signaling cascade has some logic gate. If you take away one substrate, the entire logic gate will fall apart. So AND gate is there, OR gate will be there also. For example, one gives lower response, the other gives higher response, like bistability. That is also in a way examples of logic gate. Okay. Yeah.
Thank you, Professor Das. So we'll take one last question from Ashesha Mondal, who is a semester 5 student of our department. Ashesha, go ahead.
Thank you, sir, for your informative lecture. Just like we have read about reactions that can give thermodynamically and kinetically controlled products in organic chemistry, do we have similar products in case of supramolecular polymers? In case of fuel-driven polymers, is it kinetically controlled or thermodynamically controlled or something else? Do we have similar examples in organic reactions, fuel-driven reactions or products?
Well, see, the thing is that this is again very nice question actually. So that is the question we're asking here also. Here, we are not reaching equilibrium, right? Obviously we'll all reach equilibrium. Everything will reach equilibrium at some certain point, even your kinetically controlled product. For example, a naphthalene sulfonation, right? It happens in one position and two position. The two position will be, I think the one position is kinetically stable, and two position is thermodynamically stable, right? Because of more resonance states, right? So, but in this case, we are talking about assembly. So, a structure being formed, number one. Number two, obviously, these are kinetically controlled, to answer your question, because we are adding the structures together and closing the lid of the vial. While we are closing, and then we are watching it grow. This forming structures is a function of time. So when you put a function of time on certain things, that defines it, separates it from equilibrium. Equilibrium means three things. One is there should not be any addition of energy to sustain that state, or addition of matter to sustain that state, and we don't see a change as a function of time. So equilibrium doesn't have a function of time. In this case, there is a function of time, and hence we are calling it Ashesha, right? Ashesha, we are calling this as a kinetically controlled system, okay, which goes out of equilibrium.
Yes, sir. Thank you, sir.
Yeah, Rahul, I can't hear you.
I think no more questions. Thank you, Professor Das, for your interesting lecture, and we'll move on. We are already just some time ahead of our schedule,
sure.
So we'll move ahead. And now I invite Shubhradeep, Shamashish, to take over from me. Okay.
Hello, am I audible?
Yes, Shamashish.
Yes.
Okay. Thank you, Dr. Rahul. So let's now move on to the next talk. Next keynote lecture is going to be delivered by Dr. Pralay K. Satra. Dr. Satra is currently working as Scientist D at Center for Nano and Soft Metal Sciences in Bengaluru. His research focuses on low-dimensional material for clean and renewable energy. He did his undergraduate studies at St. Xavier's College, Kolkata, before joining Indian Institute of Science, IISc Bengaluru, for integrated PhD program. He completed PhD at Solid State and Structural Chemistry Unit of Indian Institute of Science under the supervision of Professor D.D. Sharma in 2011. After completing PhD, he did Prasantama group at University of Notre Dame in US, then with Professor Stacey Ben's group at Stanford University US, and then with Professor Hakan Rensmoth's group at Uppsala University, Sweden. He then joined Center for Nano and Soft Metal Sciences in Bangalore in 2016, where he is currently working. He has published several research papers in high impact journals, mainly in the field of quantum dot and perovskite photovoltaics. For his research work, he received several awards, including the Tolusi Medal for Best PhD Thesis from IISc Bengaluru, Best PhD Thesis Award in Thank you, Dr. Satra, for agreeing to share his research interest with us. Without delay, I invite Dr. Satra to deliver his talk on the topic nanoscience in materials.
Okay, thank you, Shamashish, Rahul, and Subhadeep, and the other organizing committee members. I think you are able to hear me. Perfect. Okay. So it would have been really nice, I think, for all of us, all the speakers, to be in your college and
yes, we can hear.
Perfect. Very good. Thank you. So I also had Shamashish explained or told from my bachelor's. I was at Bankura Jilla School, and where I did my Madhyamik and Ucha Madhyamik from Bankura Christian College. What Professor Sujit Ghosh was mentioning about Bankura Christian College. I've been to Vishnupur several times, but yeah, and of course, I have a couple of juniors who are also from Ramananda College. Okay, in today's talk, I'm going to talk about nanoscience for materials research. Okay, so here you have already heard of several times about this word nano, correct? And nanoscience, in fact, the title of this conference itself has this nanoscience word. And then also materials, you have heard of it. So let us first take this point. What is materials? What is material? Okay. I need to go here. Yeah, perfect. So when you see, if you go just outskirts, you see the hills, correct? There are a lot of stones and other things. So these stones, these are, we don't call them as such as a material, but when we cut them and bring it to a proper shape like this brick, then it has become a material. That means anything which is helpful or which is helpful to the human civilization, we are calling it as a material. And does not matter, it can be inorganic material, biomaterials, so many different possibilities are there, correct? And in the earlier talk, Professor Sujit Ghosh, he talked about this metal organic framework. And then in the earlier talk, in the previous talk, Professor Dipendu Ghosh, he was talking about different biosystems, correct? And the chemistry is involved in all these cases very thickly. Okay, to give you another example, see, for example, this probably some of you have been to this place. This is I took this photograph from a place, I think in near Gorbeta, called Gongoni, correct? So this is what this picture is. It is just a soil. So this is not yet a material, but when you make a brick out of this and you make and use this brick, so for example, that is what was used for this to prepare this rasmancho, or even in, this is very famous, correct, in Vishnupur, this dal madal kaman. So that is also made from this iron. So the iron is not easily, it is not as such available as iron. So people have used this iron ore and converted it to iron, and then they are using that to make a particular device, or in this case, the cannon. So that's what the material is. Okay. So this is about the materials research. So this is, so developing anything which is helpful or beneficial for the human civilization, we are calling it as a material. Now let's come to the second part. What is nano? Okay, so first thing which comes in our mind is this nano, correct? Nano car. This is very popular, and there is a very specific reason why they have probably named this as a nano, Tata Nano. Nano is actually, it's a Greek word which means dwarf. It's small. So anything small, that's what the nano word comes. And as you know, this car was very small in size as well as in price. So people, they very well named it as nano. And anyway, in now this word nano, it has penetrated all through our society. You see, even in general articles, in research, of course, researchers and others, they're using this word nano, but as well as you will find it in, say, for news reports. For example, when this demonetization happened, there was a gaga about this nano chip. Nano chip, what does it mean? It basically means something which is very small, correct? So, so people use this word, even though sometimes we understand, sometimes without understanding, we use this. What is the technical definition of nano? So nanometer is 1 into 10 to the power minus 9 meter. And this 10 to the power minus 9, it's a very small number. If you try to imagine something which you generally do not perceive, it becomes difficult. This 10 to the power minus 9 or 10 to the power plus 9, it's such a huge number, we generally don't deal with it. We do not have a very good feeling. And so let us start to give an idea, correct? This is also Professor Sujit Ghosh mentioned that hair thickness is 100 micrometer, correct? So 100 micrometer, this is nothing but 100,000 nanometer or 1 lakh Armstrong. That is what the dimension was given. Again, these numbers, so you have to cut this hair in 100,000 times, and then one part of it will be 1 nanometer. Well, this number is also kind of a huge number, and you can't think of that, okay, you are dividing it by 10,000, 100,000 times and then taking one small part. So let me try to put it in another perspective. So this is the cricket stadium in Bangalore, Chinnaswamy Stadium. So you know the particular diameter, say that is roughly 150 meter. And then of course in the pitch, you can imagine what is the size of a sand grain, correct? So when you are in the stadium, you can feel how big the stadium is, and also you can touch one sand grain and you can feel how small it is. Okay, now we'll do what we will do, that if you try to shrink the whole stadium to a size of a small book or notebook, like A5 notebook or so, and then correspondingly, if you decrease the size in the same scale, to 1 sand grain, then that will become one particular nanoparticle. That will be in somewhere around 50 to 100 nanometer size particle. So that is 50 nanometer to 100 nanometer size particle. So you can probably get a feel that how small this number we are talking about, correct? And obviously we cannot see it in our with our naked eye. We need some other tools to seeing it, to see these nanomaterials. And of course, seeing is believing, correct? If you don't see, you don't believe. That is absolutely true. But at the same time, seeing is two different ways we see, correct? We can see it kind of direct way and kind of indirect way. Direct way means if it is in front of you, and say for example, this is transmission electron microscopy of microscopic image of some nanoparticle of iron oxide. Each of these dots, whatever you are seeing, those are individual nanoparticles, correct? And not only that, you can also collect this high resolution TM and whatever. So this whole thing is one nanoparticle. And each of these dots, type of dots, whatever you are seeing, those are nothing but these atomic columns, or it's not exactly atoms, but the atomic columns in that material, what you are seeing. So the technology has advanced so much that you can even see these atoms or the atomic columns. And this is another one where I think Samasis has also worked. This is one scanning tunneling microscope, microscopic image. This image, so each of these dots, what you are seeing, those are carbon atoms. This is taken from a pyrolytic graphite. So graphite, you know, it's a 2D, two-dimensional material. And so each of these atoms are carbon. And this, I have taken this image during when I was doing my PhD. So you can get a feel that when you are, so these are individual, these particular blips or whatever you are seeing, those are each individual atoms of carbon. Now this is, now why do we need to worry about it? See here again in this picture, in this slide, I have shown the transmission electron micrograph of a perovskite nanoparticle. Forget about what perovskite and etc. Don't worry about it. Here I want to show you, see for example, this particle, let's consider. You'll see that all these, most of all the particles are kind of square in shape, correct? And here you see this, whatever the lines you are seeing, they are kind of perpendicular to this edge or parallel to this side. But when you come to this particle, you see that they are these planes. So basically what we are seeing here is atomic planes. And these atomic planes are kind of 45-degree angle with respect to this edge. So automatically it becomes, so people are curious that are their property going to be different if you have some particle like this and some particle where the atomic plane arrangement is different. So these are the kind of questions which people are curious about, and that's how the whole technology or from this. And then next question comes that will this particle, the one which I am showing, and with respect to this one, will they have different property? So if you have a different property, then can you tune it? So there are a lot of imaginations and creative thinking are there involved in this case, and how you can basically study and then find these find their interesting property. And once you understand this material, then only you can apply it to a particular for a particular application. Okay, so let us get into the point. How do you make nanocrystals? So if you take a brick crystal and then whatever you do, basically you try to break it, cut it, chip it, etc. So you basically make it to a smaller dimension, under 100 nanometer or whatever. So and then you basically make break the material in such a way that it goes below a certain size. Then you call it as a nanocrystal. If it is a crystal, then you call it a crystal. If it is amorphous, but it is in nano dimension, then overall term what people use is nanoparticle. And this method is called top-down approach. This is what, so, and a lot of ceramic nanocrystals or ceramic nanoparticles are prepared in this method. And a lot of bulk scale synthesis are also done in this way. But all of you are chemists, or most of you are chemists, correct? So you like the bottom-up approach, or which is more as a chemist approach. So if you have to make a material, say a composition of A and B, what will you do? So you will try to find some salt which has A plus and B minus, and they will react and they will form AB, correct? And A plus, you can't buy A plus as such, so it has to be a salt of A and salt of B, and they has to be dissociated and they will form this AB, correct? So this is how we plan for the reaction. And but when you take, say for example, if you take sodium sodium hydroxide and HCl, hydrochloric acid, if you mix them together, sodium chloride crystal will precipitate immediately. But that forms in bulk. Bulk means which is in micrometer or even larger. There are of course certain more technical definition. Let us not go into that point. So you are getting a big crystal. That's what you call as a bulk system. So, but you want to restrict when this growth is happening from A plus and B minus, they come and react and formed AB, and few of these has come and formed a nanocrystal. At that point, you want to stop the reaction. And that is generally done by some passivating molecules to arrest the growth of this nanocrystal. And that also means that nanomaterials, they are primarily kinetically stabilized product. In the previous question, one of you have asked about this kinetically stabilized or thermodynamically stabilized product. The bulk material is most of the time they are thermodynamically stable, but when you are arresting the growth with the help of these passivating molecules, those nanomaterials are kinetically stabilized product. Okay, good. So say for example, we want to make lead sulfide nanoparticle. Okay, so PBS, that is what lead sulfide. Quantum dots, I'll give you the definition of quantum dots soon. So what you have to do, you basically know you have to take something which will make Pb2 plus, correct? So people generally do take lead oxide and oleic acid in some solvent, octadecene, and then when these two react, lead oxide and oleic acid, they form this Pb2 plus ion or lead oleate ion. And then sulfur precursor comes from this sulfur source. This is the sulfur precursor. So that is TMS or bis trimethylsilyl sulfide. And this reaction happens at 150 degrees Celsius or 110 degrees Celsius. And this oleic acid, it's not only dissociates this lead oxide, it also comes as a passivating molecule. So it comes and attach on the surface. It passivates the surface of this nanocrystal. And the TM image of these particles, so each of these dots, whatever you are seeing here, those are each individual lead sulfide nanoparticle with an average size of 3.2 nanometer in this case. Okay. Now, these nanomaterials have an interesting property, particularly the semiconducting nanomaterials. All of you are aware of particle in a one-dimensional box, correct? So where the energy En equals to n square h square by 8 ml square. L is nothing but the dimension of this box. Okay, very good. So you can certainly, for a given energy level n and n plus 1, you can calculate what are this En and En plus 1. You can also find delta E. Delta E, if you just do this calculation, you will find that it is inversely proportional with the L square. So as you increase the size of this box, then what will happen? The energy level difference between two consecutive energy level will come down. Clear? Very good. And this is being used for basically for to alter or tune the property of some of these semiconducting nanoparticles. So delta E is inversely proportional to 1 over L square. And then what happens? So you are aware of conduction band and the valence band of a semiconductor. So it's very, I'll just briefly tell. Valence band is, so semiconductor is basically you have a band gap. It do not have a continuous band. Correct. So this band gap, so below that, all the at 0 Kelvin, all the electrons are, these states are occupied in the valence band. The conduction band, it do not have any states. Correct. So this is what the general scenario, and this gap is the band gap. Now, if you decrease the size of this or increase the size of this particle, that means this L you have increased, what is going to happen? So from this energy, from this state and this state, this delta E is going to decrease. So what happens? This band gap of this material, of this nanocrystal will decrease. Although the property or the material is not changing, it is only the size of the particle you are changing, correct? And so similarly, if you make it smaller, then this energy gap or the band gap is going to increase. So you see that these nanomaterials are kind of unique in that way that, or semiconducting nanomaterials, their band gap is, or the optical property or electronic property is one is able to tune this optical or the electronic property of these materials. So here what I have shown is cadmium selenide nanocrystals of different sizes, correct? So this is these photographs, this row of photographs is taken under normal light. This is what it looks like. All these are cadmium selenide. It's not a different material. But when you shine UV light, then you see that the first one, it is emitting blue color, then green, and then orange, and then red. What it is meaning? So that means that here, these particle, the blue emitting particle, they are very small in size, correct? That's why their band gap is high and they are emitting this light. I'll explain briefly why they emit light. And so it is of higher energy. Blue light is certainly higher energy than green, than orange, and then red. So red emitting particle, they are the smallest size in this series, correct? And say, for example, I am wearing this blue shirt, and this shirt is made of this color is because of some dye. If you change this dye molecule or whatever, the size of this dye molecule, well, it's a molecule. The property of this molecule comes by itself, correct? You cannot alter the property of this particular dye molecule. So the color is not going to be different. You have to use a different dye molecule to change the color of this shirt. But what happens in case of this nanomaterial? You are keeping the same material. In this case, say it is cadmium selenide. The cadmium selenide remains same, but you are changing the size of the particle, and thus the optical properties of this material are becoming different. So quantum dots, this I have used this term, probably you have also heard of it. Quantum dots are nothing but semiconducting nanoparticles which exhibit quantum confinement. You are aware of quantum confinement, correct? Which exhibits basically if you go below a certain size, and then if you change the size of this particle, then they show this the electronic property. It gets affected with respect to their size. And I have explained you earlier in the previous slides that how the size variation can give a tunability of their band gap. It is not only size, it can also be with respect to composition. So basically, say you take cadmium sulfide and cadmium selenide. I am taking two semiconductors, correct? One has a high band gap, one has a low band gap. Now, what you are doing, you are mixing this particle and making one. So basically, you are taking the cadmium same, you are varying the sulfur and selenium composition. So as you are changing the composition, the band gap of this is changing. In this case, the selenium concentration is going down. That's why the selenium concentration is actually going up, sulfur concentration going down, and you see that band gap is changing, and the emission from from green, it can be tuned to yellow and then eventually to red. Correct. Now, this is also true, by the way, this is also true for bulk material. It is not only this composition change, the band gap tuning with respect to composition change, it is also, it happens in the band gap. Then this property of what do you call it, whatever the pictures I have shown so far, they're very brightly emitting nanocrystals, correct? So they have very high photoluminescence. And that is something which is not easily achievable in case of the same bulk crystals of these materials. And one can now see what I am talking about. The size of this particle is hardly 5 nanometer. So one can make, say, for example, employ different chemistry and then make different heterostructures within this nanoparticle. So here we're talking about, say, bare cadmium selenide nanocrystal, which has quantum yield is 10%. Quantum yield is what? So you sign 100 photon, correct? You sign 100 photon, and then only 10 photons are coming out as an emission. So it is absorbing 100 photons and 10 photon comes out as the emission. That's what the quantum yield. This is more as a photoluminescence quantum yield. But say, for example, you take the same CDS nanocrystal, a CDAC nanocrystal, and then on top of that, you make a coating of cadmium sulfide. There are techniques available, chemistry available, chemical methods available to make this type of structures. When you make this one, then the quantum yield goes up to 50%. That means if you shine same 100 number of photons, it is emitting 50 number of photons. So it appears more brighter. That's what it means. And again, there is another, say for example, this is a gradient structure. So the core of the nanoparticle is more of cadmium selenide, the surface is more of cadmium sulfide. So what happens here that you basically take help of take advantage of this reactivity. Cadmium 2+ has different reactivity towards selenium and towards sulfide, selenide and sulfide. So if we have done in this case that we have this cadmium salt, and then we injected both sulfur and selenium sulfide and selenide salt together. And then what happens, the quantum yield of this material, it forms like, so CD2+ has more affinity towards selenide, and thus the quantum yield, so it forms initially cadmium selenide, and then eventually sulfur, which has less reactivity towards CD2+ sulfide. So that forms cadmium sulfide forms on the outer area. So it forms kind of a gradient alloy in this CdSES nanocrystal. Well, one can use different techniques and make different types of heterostructures even within this small size. This one is zinc sulfide, it has formed at the core, and then we had cadmium selenide, which is low band gap, and then again we have this zinc sulfide on the surface, and then the outside, the blue layer is nothing but this passivating molecules, which I explained. So here, if you have heard of this word quantum dot, and this one is called quantum dot, quantum well. Quantum well you have heard, correct? So you have high band gap, low band gap, and again high band gap situation. Here everything, this high zinc sulfide is a high band gap. So high band gap, low band gap, and again high band gap. So it is forming a quantum well, and the whole thing is within a quantum dot structure. So that's what it's called, quantum dot, quantum well. Essentially, the point here to convey is that the chemistry has advanced over last 20-25 years, particularly in this field, and one can very easily and very it's the processes, the synthesis processes are so standardized that one can very reproducibly synthesize these type of structures, these different structures with high quantum yield. Okay, so this is a funny picture. I just introduced this one recently in my talk, how to make these nanocrystals suitable. Whatever we have talked about earlier, see, we were talking about cadmium selenide, that is the inorganic part of the system, correct? And then we have these passivating molecules. So one wants to see, for example, here what the picture shows that one person without any clothes, he is on the snow. So it is, of course, it is not comfortable situation probably. Whereas you see this person, he is also on the snow, but with a proper coating. That means proper dress is there. So similarly, one can modify the surface of this nanocrystal, this on the passivating molecules of the surface, passivating molecule on top of the nanocrystal to make it suitable for a particular application. So for example, if this same person with this particular attire or the dress, if he goes inside in a desert or say in summer days in Vishnupur, he will not be very comfortable, correct? He will be sweating a lot. It is not comfortable. Then the dress has to be changed. So what essentially means that once you synthesize the nanomaterial or this inorganic part, then you have to passivate it properly so that it can be used for a particular application. And that has been done extensively over the last 2-3 decades. So we are talking about this inorganic core, and this inorganic core plus organic passivating molecules. You use this. And then what happens, this passivating molecules, it plays significant role. It plays actually a role in controlling the size and size distribution. In the previous case, I talked about this oleic acid. Then it controls anisotropy. That means whether this particle is going to be a rod shape or a two-dimensional shape, or is it going to be a sphere? So those things it determines. It also stabilizes the system. That is what I was talking about. So this, of course, there is a certain one has to worry about what is the ligand. Ligand means passivating molecules and this inorganic part, the quantum dot what type of interactions they have. And by tuning this, see, for example, here I'll explain with this one. This all three, this A, B, and C, these three figures are transmission electron microscopic image or TEM image of gold nanoparticle. So when the gold nanoparticle was synthesized as such, they are very big in size, correct? So they are almost 20 nanometer and they are of various shapes and sizes. Now, when one add this thiol, R is the alkane part and SH is the thiol, correct? So when one adds this thiol, even at room temperature, these particles breaks apart and they form these small particles. Still, so the size has decreased significantly. There is a size distribution. But when they reflux it at certain temperature, 80 to 100 degrees Celsius, then the same particle transforms to much uniform size. You see, from here, one is able to control the size distribution. And what it is changing in this reaction, the change is only these passivating molecules, the thiol. If you take this beautiful, perfectly size distribution or almost monodisperse gold nanoparticle, and then you add DDAB, dodecyl ammonium bromide, then it goes back to again that bad big size and bad size distribution. So essentially, these passivating molecules, they had a lot of effect on the growth of this nanocrystal. This one is from one of my colleague at Stanford. He prepared these tin sulfide nanoplatelets. And that was, again, this platelet forms because of this particular passivating molecules, what he have used in this reaction. This is one more example from one of our colleague, Dr. Anshuman Nag from ISER Pune. So they have first synthesized the nanoparticle as such. You see this colored part, that's where the nanocrystals is there. That is the toluene part and this is the water. So they are phase separated. The nanocrystals are in the toluene organic phase. But when you add DDAB into this system, then what happens? Sorry, the toluene is the top part and formamide, which is the polar solvent, that is on the bottom part. So initially the particles were in formamide. But when they add DDAB and then shake it for a certain time, then these ligands, this DDAB go and attach to the surface of the nanocrystal. And then what happens? DDAB is a nonpolar solvent, nonpolar molecule. So it drags these molecules to the nonpolar solvent, that is the toluene. So the same particle, but by tuning this surface or the passivating molecules, it is possible to make use of it for different applications, to make synthesize for different properties, etc. This is one question I just added after one of the question where one of you have asked that how these nanomaterials can also be used for drug delivery, correct? But these are inorganic materials. How will it dissolve in water? It does not dissolve. So what people do, again, they take help of these passivating molecules. In this case, they're passivated with some polyethylene glycol. Then if you attach this polyethylene glycol, if you modify the surface of this particle in such a way, then now this whole system will be soluble in water. And people attach different types of antibodies, peptides, small molecules, drugs, etc. And then they carry this particular quantum dot to that particular system. So for example, I'm not very familiar, but you are also aware probably this antigen and antibody, they have a very specific reaction, correct? They are very specific to each other. So if you modify this surface with particular antibody, then they will go and attach to that particular antigen. And then you can use some other optical techniques. This materials fluoresces, correct? They emit light. So you can, by that way, you can probably identify, people are identifying certain types of tumors where it is located inside the body. And those things have been shown in some cases. Some examples are already established. Okay, so I have probably another 10 minutes or so, and let me talk briefly about some applications. So quantum dots, the semiconducting nanoparticles, they are exclusively... Sorry, Samasis?
Yeah, you can talk for another
8
to 10 minutes. Yeah, by 12. Yes,
Yeah,
you can go ahead.
thanks.
Sorry to interrupt.
So these quantum dots, they're used for light emitting diodes, correct? We talked about this emission. So that the LED is nothing but light emitting diodes, and people use these quantum dots for these light emitting diodes. People also use this for photovoltaics. In the next part of the talk, next 5 minutes or so, I'll be talking about how these quantum dots can be used for photovoltaics. And you see photo detectors. Photo detectors also, it can be used because this material, they absorb light, correct? So if something, you are making a photo detector, that means it is a detector of photons. As these materials absorb light, so it can be used as photo detectors. It is used for catalysis and other systems, as well as biomedicine and environment. And these things are not only in research state. There are some of these are already available. I searched today in Amazon and Amazon India, and this is quantum dot QLED, quantum dot LED TV. LED TV we have heard, and also probably some of you have heard of this QLED TVs, correct? So this is from OnePlus, that company. Some of you have probably mobile from OnePlus. So they have this TV which is made of quantum dot LEDs. Okay. And here the color purity is much better compared to the previous generation systems like LED or LCD type of system devices. Of course, these systems are as of now very expensive, and there are several reasons. For example, one has to develop particular synthesis strategy to do a bulk scale synthesis, whereas maintaining this the same size or size distribution, correct? As I said, that as you change the size, the optical property changes, correct? The color changes, emission color changes. So if you are synthesizing a particular nanomaterial, say you want to emit only the blue color, but if you have a very broad size distribution, then those quantum dots are going to be emitting both blue color as well as green as well as probably red. So it is not going to be helpful, correct? So size distribution or the development, size distribution is very important, or the size, both size and size distribution. And the development of the synthesis, particularly in bulk scale synthesis, that becomes very important for the actual industrial application. In several cases, whatever previous speakers as well as in our group, when we do research in our lab, those are very small scale synthesis we are starting the optical properties. Of course, there are several other groups of researchers, those who take this type of material and they try to develop strategy how to improve the synthesis to a much larger scale, and those are very important for actual industrial applications. Okay, good. So briefly, we get most of our energy from sun, correct? So the coal or whatever we are using, coal or natural gas, those probably from the sun millions of years ago it came, and whatever it transformed to these fuels. But we are talking about, when you talk about renewable energy, then we want to convert the sun energy to for our to useful energy, correct? Sun's energy, but sun's energy, it comes from in form of light, but and that of course that generates a lot of heat, correct? So, and we used a lot of this, even directly the sun's energy we use in several cases. And how I'll give you this example of salt mines, where we use a very simple technique to choose that particular, how to improve this method. Okay. Anyway, if you keep a bucket of water outside, then it gets warm and eventually it will evaporate, and then one day it will vanish. Depending upon after some time it will vanish. Correct. It will evaporate entirely. So this picture is a salt mine in Gujarat, somewhere in Gujarat near Kutch area. So, and this is another one. This is, you see this colorful, these are also some salt mine, potash mine, basically. This is in Moab in Utah in United States. What are these colors? They particularly add some dyes, and these dyes are nothing but you take gems, correct? Some of you have taken gems, and this blue color, whatever you are seeing, the same edible dye they add. And that particular molecule is called brilliant blue FCF, correct? You see this absorption spectrum, correct? So this is only simple absorption spectroscopy, and that the maximum absorbance is at 630 nanometer. Now, why they have particularly used this dye? The reason, if you look at the solar spectrum, this is what the solar spectrum, that means at a particular wavelength of light, what is the intensity falling on Earth's surface. And you see that 630 nanometer is somewhere matching with the maximum region, maximum intensity. That means this material will absorb a lot of sunlight, correct? If you have some material which has a band gap or absorption age, or this peak is somewhere around 1490 nanometer, it is not going to absorb light. Although it should absorb, but it will not absorb because there is not enough intensity, correct? So, but just by using this dye, one is able to absorb much higher amount of light, which converts to heat, and that makes the process much faster. So just simply looking into the absorption spectra of this dye molecule, one is able to efficiently or make the process of drying much faster, or evaporation of water much faster. Okay, so how do we use energy? If you look around your room, you will find that we have a lot of electronic gadgets, and whatever the way we are doing, I'm presenting through my laptop, you are watching through your mobile, that requires energy and electrical energy, correct? And all the lightings, everything. So a huge amount of energy goes for this, electrical energy goes for transportation, for our agriculture, as well as for lighting, correct? So we want to use electricity. And the way we are getting light, we are getting energy from sun is through light. So we need to convert light to electricity, and that method is called photovoltaics. Okay, so let me not go into the details of this. Of course, you are aware of silicon solar cell, and of course there are the other thin film systems like cadmium telluride, CIGS. It means copper, indium, gallium sulfide. There are a few other systems people are working. In fact, my lab here in Bangalore, we are working on some particular system called lead sulfide that I gave an example, and also some perovskite nanocrystals. There we are using, we are trying to synthesize new type, and how we can make it more efficient solar cell using this new material. Okay, so let me come to this point, which I have talked to you earlier. See, we talked about this valence band and conduction band, correct? And this is the nanocrystal. So it has a band gap of say 2.4 eV, or a little more than that. That means this is the gap we are talking about, 2.4 eV. If we shine some light, which is higher whose energy is higher than the band gap of the material, then what will happen? Valence band is filled with electron. This electron will absorb that photon, and then it will go to the conduction band. If you put higher energy, then this electron will go much higher up, and then eventually it comes to it does the vibrational relaxation. That means it interacts with the phonon, and phonon coupling, that's what people use the word. So basically it heats up the system, correct? And then what happens when it comes to the bottom of the conduction band? Then there is no more energy state. Then what happens? This electron, it recombines with the hole in the valence band, and that time equivalent amount of energy it gets emitted as photon. And this is what the photoluminescence process we are talking about, correct? And the quantum yield earlier, whatever I talked about, how many number of photons you are shining and how many photons are coming out, that is what the definition of the quantum yield, that's what it measures. Now you see that this electron, whatever it has absorbed this light energy, correct? And now it is at higher energy. And there are techniques, and if you can basically, this electron is at higher energy, and if you can harvest this electron instead of recombining and getting this light out, if you can take this electron through a circuit, external circuit, basically then you will be able to make use of this electron energy and generate electricity. I'm not going into the details how one can do all these things, but it is possible, and that's how a lot of nanomaterials are being used for photovoltaics. So photoluminescence, it's what we talked about, is the recombination of this electron and hole. Photovoltaics is nothing but the separation of this electron and hole from this system. Okay. Good. Not only photovoltaics, we also employ a lot of these nanomaterials for sensors. This is one example which we have developed in our lab. My student has developed. These quantum dots are manganese dot zinc sulfide. So we spin coat on very thin layer on top of some carbon nanomaterials, particularly called reduced graphene oxide. Okay, you have heard of this graphene word, correct? Graphene oxide is nothing but, so Graphene is only C, correct? And then graphene oxide, basically you oxidize that system, and reduced graphene oxide is basically somewhere in between. It's a reduced graphene oxide. It's not completely graphene oxide, or it's not graphene. Anyway, so on top of that, we add these nanomaterials, and they have some luminescence. And then when we are adding 1 drop of lead, then you see this emission is quenching. So the emission is gone, and that's how one can detect this lead. So it is possible to sense this system. Okay, so in this talk, what we have learned what are nanomaterials. Correct? We have talked about what materials and what nanomaterials. We talked about quantum dots and semiconducting nanoparticles, how their optical properties of quantum dots change, and how briefly I have mentioned how quantum dots can be used in photovoltaics. Okay, so as most of you are doing your undergrad, so it is very nice. A lot of your college teachers, they have or most of them have experience in research. So try to get the students should get some experience in to do some sort of experiment, some research you do. Correct. And then there are, of course, different fellowship are available, including ISER, CNS, different IITs. So write some applications, write some proposal, and get some fellowship and do some experience in research. And there are, of course, possibilities for you for Inspire Fellow, correct? And see, you are in chemistry, correct? But being chemistry, you can continue. Some of you, I'm sure, that will continue your PhD research career in research. You will do PhD. So from chemistry, you can go to chemistry, material science, nanotechnology. One can also do computational material science, biochemistry, biotechnology, bioinorganic chemistry. There are a whole lot of possibilities available when you are coming from this chemistry background. And several interdisciplinary fields are also emerging. So look out for those, what interest you. But whatever you do, remember one thing, that if you have a very strong base, what you are doing at this BSc level, if you have a very strong base, you can, does not matter whether you go in academics or in industry, or so you will have always an advantage. So make your base very strong, and at the end, enjoy whatever you are doing and have fun in doing, or in reading, or even in attending classes. Okay, so with this, I'll end. Thank you for your attention. And this is my contact information, pshantra@sense.res.in. If you have any question, please feel free to write to me. Thank you.
Thank you, Dr. Shatra, for a very wonderful lecture. Actually, Shamasis has some audio issues, so
sure,
he's unable to take over from here. So I will just take over from here.
Sure.
So if anyone has any other questions, students, please raise your hand. Okay, Dikpriyo, he's a 5th semester student from our college. Please go ahead, Dikpriyo.
Thank you, sir, for your very informative lecture. Can you please explain the advantage of quantum dot solar cell over commercial PN junction side diode solar cell?
See, even when I am saying quantum dot solar cell, in several, I have people also use this material for PN junction. PN junction is a technique, or it's the not technique, it's the operating principle, correct? So one can make this quantum dots P type, and then put it on top of N type material, and then PN junction solar cell are being used, even using quantum dot. The next point comes that what is the advantage? Now, when you look for silicon, say for example, silicon solar cell, silicon, one has to use a very pure, very high pure, 99 point, please count how many nines I say, 99.99999. I think I said 5 or 6 9. So that is the purity of silicon one has to prepare. But silicon solar cell is still the best solar cell, best one or commercially available in the market. But this technology has developed over the last 70 years, and that is where it is there. People are trying to develop new materials so that one can make these devices much cheaper way. Correct? Why don't we use solar cell today? Because the cost is more. So how it will be only in market when the cost is less, correct? You will not go to the market and buy something which is expensive, whereas something you can get with a less price and the same capability, correct? So it's not about that why quantum dots. So quantum dot solar cells are not really in market as such, but people are doing the research so that one day it can beat the silicon solar cells. I hope I'm able to answer to your point. I said a lot of words. Anyway, yeah.
Thank you, sir.
Yeah. I think Ritik has some question. There I see the hand up.
Ritik, go ahead.
Sir, first of all, thank you, sir, for your very informative lecture. Sir, as you mentioned about passivation of nanoparticles, so which types of chemical are used as passivating agent?
Okay. See, for example, it's not depending upon what system you are developing. I'll give 2 examples. Correct. Say, for example, you are making lead sulfide. Lead sulfide nanocrystal, the way one does the synthesis, they're also. So when we do the synthesis of lead sulfide, we take excess amount of lead in the reaction. Correct. So Pb2 plus is much higher in amount. So the surface of this nanoparticle is going to be lead rich. Okay. Then what you do, you select some passivating molecules like oxalic acid, so COH, carboxylic acid group, correct? And they will bind to this Pb2 plus. So that is the type of passivating molecule one use. There is also, but this passivating molecule it's very long, 18 carbon chains, so it becomes insulating. Then what people do, if you want to use this lead sulfide for some solar cell application, then you need a good conductivity, correct? So they want to retain the passivating molecules, but they decrease it to mercaptopropanoic acid, MPA. MPA, what it has carboxylic acid as well as it has thiol group. So this thiol group, one side of this passivating molecule, it can attach to this lead sulfide, and the other carboxylic acid side can attach to another lead sulfide. So it forms a binding between these two. So the conductivity of the system improves, and that's how one is able to make use of it for solar cell. If you use lead sulfide with oleic acid, it does not form, it is insulating film, so one cannot use it for the photovoltaic application. Next one, for gold, if you take for gold nanocrystals, and if you take carboxylic acid, it doesn't have any interaction, so you will not be able to use it as a passivating molecules. But gold and thiol has a very good interaction, correct? So people use thiol molecules for the passivating the gold nanoparticle. So last example is that if you know that the nanocrystal what you have synthesized is negatively charged means, say, this lead sulfide, it is more of sulfides are there on the surface, then you have to choose some passivating molecules which are positively charged, like phosphonic acid, correct? So depending upon the application or what you want to do, you have to tune the material, tune the passivating molecules so that it suits that application.
Okay, sir.
Yes, next one.
We have one question from Pameli Ghosh.
Yes.
Please go ahead.
Yes, sir. Thank you, sir, for such an excellent lecture. So my question is, what is spin-coated nanomaterial? How can I prepare it? How can you prepare it?
Spin-coated, correct?
Spin-coated.
S-P-I-N.
Yes, sir.
Yeah. So spin coating spin coated nanoparticle and spin coating are 2 different things. Nanoparticles is what we talked about, correct? Spin coating is a method. So there are different ways you can these nanoparticles are in solution, right? You have to put it on some substrate. So how do you do that? You use different technique. One technique is that you can take the solution, you just drop it, let it dry. That's what called drop custard system. Spin coating means something is rotating at high speed, say 2000 to 5000 RPM or whatever speed, correct? And then you add this solution, this quantum dot solution. Then what happens? It forms. So as soon as you spread it, as soon as you drop that solution, it spread throughout that substrate. And then it forms a very thin layer. By controlling the speed of this rotation or controlling the concentration of this quantum dot solution, or choosing what type of solvent where you have dispersed the solvent and the substrate where you want to deposit, those things determine what is the thickness it is going to be. So if you do a spin coating of these quantum dot materials and get a thin layer on the substrate, then you will call it as a spin coated nanoparticle.
Okay, thank you, sir.
Okay, Osesham. Asisha Mondal, our student from 5th semester, has one question. Please go ahead, Asisha.
Thank you, sir.
Asisha, you want to ask something? Okay. Yes, go ahead.
Sir, can you explain briefly how nanoparticles are imaged in a transmission electron microscope?
Okay, it is nothing special with the nanoparticle. Okay, let me first tell you, and then I will come to how TEM works. Basically, transmission electron micro. See, you cannot use light, correct? Why you can't use light to see these nanoparticles? Because the wavelength of the light, visible light, is how much? It is up to 400 nanometer. You can use some UV light, then 300 nanometer, let's say. So if you want to use the same, so if you want to probe something, the lambda, that means the wavelength of that probe, should be and the image particle what you want to image, or the feature what you want to image, should be of the same dimension. So it should be of lambda value, correct? But here we are talking about something which is much smaller than the wavelength of the light. So this is something called diffraction limit, and one cannot use visible light to probe this smaller feature. So the way it is done is taking electron, higher energy electron. You can tune the energy of the electron. So when you are using this small wavelength of electrons, and they are interacting with the sample. So you have this sample, you pass the electron, and then whatever the electrons are transmitted, that is what you put it in a detector. That's why it's called transmission electron microscope, correct? And of course, very similar to your optical microscope, as you have a collimation and then focusing on the sample and then again focusing on the detector. So those things are also done in case of transmission electron microscope. Instead of the photon, you are using electron for transmission electron microscope.
Yeah, I have one questions. Shamasis, can I?
Sure.
Yeah, so I will just go ahead. So the thing is, you briefly mentioned about the anisotropy there in your slide. So we know about anisotropic behavior. In terms of magnetism, we see sometimes in magnetic materials. And what kind of anisotropy you try to explain means you see in your materials?
Here, anisotropy, what I meant is the shape anisotropy. Correct?
Okay.
It's the shape anisotropy. And just for the sake of, I think I have answered your question, but for the sake of the students, I'll explain a little bit more. See, for example, you are synthesizing a material, correct? And it is forming a crystal. That means, say, if it is it's a very bad example, but let's say you can see my hand. Say this is 100 surface, okay? This is 10 surface, and this is 001 surface, correct? Now, if you choose a passivating molecules in such a way that they bind to this surface very strongly and they do not bind here, then what will happen? These surfaces are bound, so no other reactant can come and react on this surface. They will only react along this surface. Then what is happening? The growth is happening along this direction. That means you are going to get the growth along this direction. So if this surface and this surface and this side surfaces are identical, whereas this surface is different, then you are going to get a rod, correct? Or similarly, if the preferentially it attaches to this surface and the bottom surface, then you are going to get a plate. So that's what the shape anisotropy one can get from by choosing a particular type of passivating molecules.
Thank you. I also wanted to mention that the way you have structured your talk, it's really great. It was a wonderful lecture.
Thank you for organizing this. I thank all three of you primarily.
Okay, thank you. Okay, thank you, Dr. Satra. It was a very interactive session, also it turns out to be. So we are running behind the schedule. Am I audible? Okay, so I'll just now ask Rahul, I think, to introduce the next speaker. Rahul, can you hear me?
Yes,
there is a connection issue, I guess.
Little bit breaking. Yeah.
Okay, Rahul, you can take over. I should
Okay, okay. Okay, thank you, Shamashish. I'll take over from here. So it is my pleasant duty to introduce the very next speaker, and also this is a very new session where we have 3 young scientist lectures. And the first lecture is to be delivered by Dr. Manoj Panda, who is presently an assistant professor of chemistry, Jadavpur University, Kolkata. He's working there from 2019, and he did his BSc honors from Vidyasagar University and MSc from Jadavpur University, and later completed his PhD in chemistry from IIT Bombay. And before joining Jadavpur University, he was a postdoc fellow at Dow Chemical as well as in University of Crete, Greece, and later a postdoc associate and a research scientist at New York University, where he worked with a very young and dynamic faculty, Professor Panchen Amov. And later, after that, he joined as a scientist fellow and assistant professor level at CSIR NIST Trivandrum. And he has published in very high impact journals, including Nature Chemistry, Nature Communication, JAX, Angewandte, to name a few. And as a PhD scholar, I was really overjoyed reading his paper on plastically bent molecular crystals, which inspired me a lot. So several of his research works have been highlighted in scientific forums like Nature India and other places. And he has also been recognized as one of the emerging investigators by the Journal of Crystal Growth and Design. So today, Dr. Panda is going to share with us the fundamentals and applications of bio-inspired smart materials. So I just, you can understand there is a lot of background noise coming in West Bengal. So please take over. Thank you.
Okay, thank you, Rahul. Thank you for your extensive introduction. In fact, Rahul was a good, what should I say, junior when I was in CSIR NIST, and he was one of the talented PhD students with Professor Ajay Ghosh. And in fact, he did a lot of good work during his PhD on the material science perspective. And he also done some extensive work during his postdoc. Anyway, thank you, Rahul, for inviting, and thank you, organizing team of Ramananda College, for inviting me for this lecture and giving me the opportunity to present my work. So let us share the screen first, and then I'll start talking. So am I visible? My screen is visible to all of you?
Yes.
Yeah. Okay, and you can hear me also properly, hopefully. And do knock me if you do not, hear me properly. Anyway, so Rahul has already introduced the title of my talk, which is Bio-Inspired Smart Material, and considering the students, the audience level, I mean undergraduate student, mostly undergraduate student, as well as other students are also there, and other audience are also there. But I guess its majority is undergraduate students. So I will try to focus my talk on the material that are inspired by nature, and how the natural nature is actually inspiring or helping scientists to develop new technology. So student can take some idea or take some knowledge to choose their future career in science. So whenever we are talking about science in my laboratory, that means there are some people who are constantly working in my laboratory, which these are my PhD students, and I should acknowledge all of them. And Prasenjit, Dibyendu, Shovi, Ranajit, whatever the work I have done, I will be presenting here, has been done by them, and as well as my past group member from CSIR NIST. Although I did not have a PhD student over there, but I had some MSc students. I acknowledge all the MSc students and interns who have worked with me, and the Department of Chemistry, Jadavpur University, for giving me lab and office infrastructure, etc., and funding from UGC, funding from ACRB, and obviously all my collaborators. So, so this I should be, acknowledging all of them. Now, coming back to the title, Bio-Inspired Smart Material. Why we are inspired by biological material or biomaterials, and why they are called smart materials. So, Before actually going to actually research, research part, I will introduce what is called bioinspired and what are called smart materials. Now, whenever we are calling bio-inspired, that means that we are inspired something from biogenic. Biogenic means that generated from biology or from environment, from nature. Biogenic smart material. And there are many examples in which these materials or technology, smart materials and smart technology has been developed from the inspiration of biological organism or biological natural objects. So here I'm listing only few examples, but there are many more examples. For example, the Shinkansen, the Japanese bullet train, all of you probably know, and India has also taken up a project for bullet train. But there was a difficulty of designing bullet train. Normally you can see the trains are actually flat shaped in the front, and because of which it was getting a lot of noise when it is going. It was actually colliding with the air because it is very high speed, and especially when it is going through the air, or especially in the tunnel where the suddenly air pressure comes in or comes out, then there are a lot of noise, and that was actually avoided by simply taking the idea from Kingfisher beak. As you know, Kingfisher beak are like sharp beak, and they can dive in water very silently for catching fish. And if there are too much noise, fish can go away. So, in order to minimize the sound of colliding with water, so their beak shape is so that it can very silently they can dive into the water. And based on that idea, I think Shinkansen trains have been, the frontal shape of the Shinkansen or the bullet train has been developed, and after that actually that problem is very much solved. And there are many other. I'm just showing one by one, like Barak sheet. As probably I don't know how many of you know, a Swedish scientist, mechanical engineer scientist, George D. Mestral, when he was going for a walking on the hillside, and he saw that some kind of seeds which are attached to his coat and pants, and with his dog's skin also. He was walking with his dog, and finally he come up with the idea of the Velcro, which is one of the most useful material in current technology. The use of Velcro, probably all of you probably know where it is used in the shoes, tightening kind of adhesive, temporary adhesive for shoes, bags, and many other things, even the dresses also. Okay. And this one is lotus leaf or taro leaf. আমাদের বাংলায় যেটাকে কচু পাতা বলি, lotus leaf, পদ্ম পাতা এবং কচু পাতা. If you see they are very much hydrophobic. That means they do not hold the water. The water can slip away from their surface. And I think Rahul can give you the better answer because he has already worked in this area. How the a natural hydrophobic surface can be made, and what are their critical angle, contact angle. How you can manipulate. So this another example is gecko's feet. How the gecko means যেটাকে আমরা বাংলায় টিকটিক, actually not the same species, but it's slightly larger species, gecko টিকটিক যেটাকে বলি. How they defy gravity, how they defy their body weight even when they are walking in the rooftop. And that is mainly rooted to their nanostructure, which can actually combine with the wall by several intermolecular interaction, kind of van der Waals kind of interaction. And because of that nanostructure, actually they are able to attach to the wall. And based on that, actually different types of material like trekking shoes and many other materials has been developed which can prevent the slipping of the shoes or slipping of the surface. Okay, and the other one is so sorry for the sound actually. The chameleon material which can change color with the environment, from which the photonic crystal has been developed. And as you know, this is just one example. There are many other examples also. The photonic guanine crystals which are used for grooming purpose, and many other materials has been used. Okay, I'll skip that. It's a lot of sound. So coming to the definition of smart material. So the previous slide was the only few examples of the materials or technology that has been inspired by nature, but there are many other. If you just go around the literature or many any other journals, magazines, etc., you can see there are plenty of examples. But our interest is mainly on chemistry, so not everything is rooted to chemistry. And since we are chemistry, I will focus my talk only on the inventions or only on the materials that are very relevant to our research, which we are doing in our laboratory. And I hope the students, undergraduate students, will be able to absorb something from my talk. And so here is the title contains a word which is called smart material or smart system, which is bio-inspired. That means biologically inspired smart material. Now, what is smart material? What we generally called only material that the previous speaker, I think Dr. Praloy Satra has already nicely discussed all those basic fundamental things about materials and how they can characterize the material. But I am slightly shifting away from that, topic. So it's a smart material. What is called smart material? That means a material which can respond properly with the environmental cue. Cue means stimuli. What are the environmental stimuli? There are different types of environmental stimuli, or you can artificially provide them, which acts as input energy to this material. And these energies are actually light energy, which you can get plenty of light in the nature and plenty of heat energy from the nature. Sound, humidity is one of the important stimuli for the nature. So basically humidity, heat and light, these are the main three stimuli that are present in the nature, and that are being utilized very nicely or very systematically or very, what should I say, very systematically by the smart material system that are present in biogenic materials, biological material. And we call it smart material when they can utilize all these input energy and provide an output energy in terms of different form. It's a kind of conversion of energy. All of you probably know about the conversion of energy, that one form of energy is converted to another form of energy. So energy transduction. So there is no destruction of energy or generation of energy. It's a kind of conversion from one system to another system, or one form of energy to another form of energy. And if a material or system can utilize these input energy which are present in the nature or environment, or you can provide them artificially, and then they can give you the output as kind of shape change or actuation. Actuation means the displacement, different kind of drastic shape change, or going from one place to another place, displacement, actuation. Then or color change, or any other property change like hardness change, viscosity change, or density change, or their elasticity change, any other kind of physical property changes, then we call them as a smart material, because these are the materials that can be used for developing new technology. For different purpose. Based on the requirement, we can utilize those materials for developing different technology. For example, if I need to change something which can change shape, and so we will be using material which can this kind of material which can change shape in presence of different environmental cue. But in today's talk, I will mainly focus on the actuation. That means a system which can actuate themselves. Either they can change the shape, or they can move from one place to another place, or they can drastically bend or split or burst away. All those things that can happen when you are providing them a kind of natural stimuli or environmental stimuli such as light or heat or humidity. And mainly I will be focusing on the light, because after coming to Jadavpur University, I have started this project on that is the main project that I am executing, which is the light responsive actuation or movement of the material, so-called smart material. And being a chemist, I always go for molecule, because everything starts from molecule for a chemist. chemist, and we need to start from the molecule. How from the bottom level we can go to the top level of smart material. But before going to the smart materials or smart actuators, let me define actuator. What are actuators? Probably some of you know, all the undergraduate students who are in the audience, probably all of you know what is actuator. Actuator is nothing but a material or a system which can transform one form of energy to mechanical motion. And the types of mechanical motions is actually called actuation shortly, but there can be different types of actuation or mechanical motion, kind of rotation, linear movement, shape change, like bending, blooming, all this kind of thing, or jumping. So all form of kinetic energy. So any other form of energy is transforming into kinetic energy. So that is so-called called actuator. So a material which can do this function is called actuator, and so that is actually a good platform for energy transduction. Energy transduction means transforming one form of energy to another form of energy, and in this case the output energy is mechanical energy or kinetic energy. Okay, so in biology, this is a kind of patented slide I present everywhere. Those who have attended my talk probably telling that this guy is presenting this slide everywhere. But this, I love this slide because this slide actually summarizes the different types of actuation that are present in nature. And it gives us immense inspiration or immense, idea how can they do these functions so easily, even though we are, facing very hard time in laboratory to develop a artificial actuators, molecular actuators, or and polymeric actuators. But biology is doing it very easily and very delicately, and that's a result of thousands or millions years of evolution and the structural evolution, what you can say, because of which they can function so delicately. Okay, so let's see the first one. The first one is corn sprout. By the way, all these videos are taken from YouTube and different sources. I have just collected for the presentation purpose and for making you understand what the importance of this research topic. Okay, so the YouTube link is already given below. If you want to see individually, you can go and check all these videos. So this is the first one is the actuation by light. The corn sprout, the sprout when they just started to grow, and they are very much they show very much phototropic nature. Phototropic means they are moving in response to light. So there are different types of phototropic movement, also positive phototropic movement or negative phototropic movement. I think biology people know better. Positive means the movement is towards the light, and negative means movement is away from the light. So there are different mechanisms for that. I'm not going to the details for that. I will discuss only those which are relevant to my research area that I will discuss later. So this is a kind of phototropic movement, and this the other one, the second one, which is the clover plant. Bangla jetake Susni shak bole. As you can see, the leaves of this clover plant is opened when the sunlight in the daytime when the sunlight is there, but depending on the sunlight they can open and close. In the night time you can see they are completely folded. Their lips are closed. So since the intensity of the light is too small, that time they fold their lips. Sunflower plant. This I need not to mention what is sunflower plant. They always faces towards the sun. Probably all of you know all these things, how sunflower plants work. The other actuations are actually pressure-induced actuation. The venous flytrap. Their lips are shaped in such a way that when some pressure is applied to the lips, they actually close very quickly, and that is so fast. Is one of the fastest actuation observed in the literature for the plant. The next one you can see, which is Mimosa pudica, the touch-induced or the pressure-induced movement of the plants. Lojjavati lata Bangla jetake boli, the Mimosa pudica. Okay, so all these are actually the internal mechanism is really fantastic, and if you go through each of these materials and read a little bit about that, you will be wonder how these the plant have developed this kind of technology and why we cannot follow this, or why we cannot develop this technology in our laboratory so that we can develop smart materials and smart technology. So that's the biggest inspiration from the nature we should take it from. So coming to my research activities, the research activities that we are carrying out in our laboratory, which is light fuel. The first one obviously is stimuli responsive fluorescent switching material that I will discuss later if I get time. But the first I will discuss only this one, the light fuel actuating material. That means the material which was developed from a molecular material which can undergo this actuation, that means different types of movement in presence of light irradiation, either UV light or visible light depending on the material. Okay, there are other research areas also where we are working, but that I will not be able to cover in this short talk. I'll try to be more precise on this part only. If I get time, I will only discuss this fluorescent switching in the last part. And the last work we have recently started, the film composite material, composite nanocomposite films that can undergo actuation. So these are the mainly crystalline material, the second part of the first part of my talk. But if I get time, I will also cover this one, the film actuator. We have recently started and successfully executing, but not yet published yet. Okay, so coming to the light fuel soft actuator. So since we are chemists, we always start from a molecule. Synthesizing a molecule is our hobby, and synthesizing new molecules, obviously with certain rationale, not blindly. We can design a molecule with certain hope that okay, this molecule will work very nicely for this purpose. At least in my case, it is a light responsive activity to show. So what is light responsibility? How you can induce this light responsibility in the molecular state, and how it actually shows macroscopic actuation. Macroscopic actuation means in the bulk scale, larger scale, the one which you can see in the naked eye. Okay, so generally everything starts from molecule. A molecule has to move first, and then it will amplify to the macroscopic scale. Okay, so light and the motion, and there should be a molecular change which should be triggered by light energy, which is the input energy, and that molecular change must be amplified to state-wise, amplified to supramolecular stage. That means 1 molecule to 1,000 molecules, 1,000 molecules to 10,000 molecules, then 10,000 to 1 lakh molecule, and then all the molecules which is present in that a macroscopic entity, let's say crystal or amorphous material, whatever it is. So then we see the macroscopic movement. But in between that, this thing, molecular change to macroscopic change, there are many other steps that are involved that might be difficult for you to understand. But what I say, that light triggered nanoscopic molecular motion caused by geometric isomerization. What are the geometric isomerization? Like cis-trans isomerization, or there can be conformational change. There are many molecules which undergo this kind of geometric isomerization, like cis-trans isomerization and conformational change induced by light. Because for any kind of conformational change or isomerization, you need energy. One need to provide energy for changing its shape or changing its color, because everything is involved in energy, and that energy is provided by the light of appropriate wavelength. In this case, in my case, it's 390 to 375 to 390 nanometer, but that's not the standard. Whatever the energy necessary for your system, you have to provide that light. And how will you get that? You just record the absorption spectra of the material, and then understood which light it is, in which region it is absorbing the light. And then you do all the associated research with this. Now, geometric isomerization, conformational change, or any kind of photochemical reaction like cycloaddition reaction. All of you probably read about cycloaddition reaction, photochemical 2+2 cycloaddition, 4+4 cycloaddition. All those things can happen in solid state macroscopic material, because of which a molecular movement is amplified to macroscopic movement. So one molecule, which is when a cis-trans isomerization occur in one molecule, a single photon comes to single molecule. That molecule actually start isomerizing, and that has to induce motion to the next molecule, which is also associatedly induced by another photon. So that cooperativity must be there in order to amplify the nanoscopic molecular motion to macroscopic motion. And that is very important. If a molecule say, no, I will not cooperate with another molecule to propagate the motion from one molecule to another molecule, then it is not going to happen. The nanoscopic motion will dissipate in the nanoscopic level only. So that is happen mainly in the solution or most of the photoactive molecules. Only very few molecules which is armed with certain supramolecular functionality, and the functionality that can engage with supramolecular interaction, and those interactions which are cooperative in nature, that are able to show kind of macroscopic actuation, that they can amplify the nanoscopic motion to macroscopic motion. Okay, that means in the bulk scale. Okay, so that's the summary of how we can achieve. But here are some of the examples of molecules. The azobenzene is one of the most common example which undergo trans to cis isomerization, and because of which you can see this kind of photoresponsive property in azobenzene molecule. Stilbene molecule also show this kind of cis to trans isomerization, and most of them are reversible, because if you either provide another light of another wavelength, or you can provide heat in order to achieve the reverse reaction. Okay, so all of you probably know it's a P-type reactions or T-type reactions, thermal reversibility, T-type. Okay. Needless to mention here that this kind of isomerization also occur in our retinal system. The fact that we are talking about bio-inspired research, excuse me, bio-inspired research, so I feel that everything is related to at least some of the biological material that we are experiencing, in everyday life. So those who know that that our retinal system, the eye system, the vision process is also a kind of isomerization, and where a molecule which is actually called retinal, is a chromophore, which is a chromophore retinal molecule which undergo this kind of cis to excuse me, this kind of isomerization, geometric isomerization during vision process. When the light falls on it, and it undergoes this kind of isomerization process, which is connected to the opsin protein actually. Okay, and this vision process is also a kind of cis to trans conversion for your information, because the way we are talking about the light responsive transformation, I thought it is important for you to resemble the fact with your vision process where the similar cis trans isomerization is happening, because of which you can see actually. Okay, so moving forward, so here is one of the molecule that we have recently developed and is reported. We recently published in Christians.com. It's a kind of acyl hydrogen-based photoactuator. Acyl hydrogen means it's slightly different from the azobenzene or stilbene molecule, but it still have a double bond which is connected to a cyanovinyl CN moiety, and this double bond is able to undergo trans to cis isomerization. In the initial stage, it is trans, and when you irradiate with a UV light of 390 nanometer to 370 nanometer light, it undergoes geometric transformation to form cis isomer, and it can reverse back by heating also. For heating at 100 degrees centigrade for several hours, it can reverse back. Apart from that, we have also observed there is a kind of topochemical reaction. Topochemical reaction means the reaction which happens on the surface. Okay, so these 2+2 cycloaddition reactions also occur between the double bond of one molecule with double bond of the another molecule, and because of which we get this kind of actuation. So these are the inner mechanism, that means the molecular level mechanism that I just outlined, but there are many more things which I'll be discussing in the subsequent slide. So if you irradiate the light on a specific face of a crystal, so let's say this is the crystal of this molecule, and here are the faces. Faces means the wall. Like if you consider a brick as a crystal, the two opposite walls are the two opposite faces of the crystal. Imagine yourself that you are holding a brick and two parallel walls of a brick are two different faces of the crystals. Okay, so for example, this is 001. So those who have slightly read about crystallography and crystal things, they will be able to understand what is 001 phase, what is 00-1 phase, and 010 phase, and etc. So I'm not going to go over details for this. And so basically, the summary is over here is if you irradiate light on a specific phase, it moves away from the light, and you can again manipulate the light direction and the light irradiation on a specific point in order to change its shape and movement. So when we show it under a fluorescence microscope, which we utilize actually UV light to see the material, we show that molecules or the crystals are actually green fluorescent, and as the time increase, the irradiation time increase, you can see there is a movement of the crystal and certainly flipped around, as you can see from the video. The green fluorescent crystal which is moving around and certainly flipped. And
Dr. Panda, I am just interrupting. You have 5 minutes left. Okay.
Oh, okay. 5 minutes left only. Okay.
Yeah, it's a 30 minutes talk. Okay. We'll keep some time.
Okay. So moving to this video, this observation actually actually prompted us to do more experiment. As you can see, we can irradiate from different phase or different direction, and you can make the shape as you want. So this straight crystal has been made U-shaped crystals. So I am not going to show the full video because it's a long video. You can see how this video how this material can be bent like U-shaped. And one of the most important thing is the elasticity of the crystal. Generally, you consider a crystal as a brittle object, but this crystal, you can see how elastic it is. It can bend almost to U-shape, so more than 200 degree, and it still remains intact. The crystal integrity remains intact, and here also you can see different shape you can achieve by changing the irradiation direction. Okay, so once you can change the irradiation direction, or you can change you can change the irradiation places, you can make it into different shape. So here are the another videos also. You can make it a hook shape, so that you can make some kind of attachment or weight lifting purpose. You can make it kind of hook shape. So there are the different types of video that we have recorded for practical application, and I'm not going to show everything in detail. And this is a kind of shape reversibility. Once you bend with the light, how can you reverse back to the original position? By using thermal energy. So these crystals, you irradiate with the light and bend it, and then you keep it at 100 degrees centigrade, and it can come back to the original shape after 6 hours at 100 degrees centigrade. Okay, so moving first little bit, here are the characterizations by NMR and UV, EXRD, IR. We can understand that these are a kind of geometric isomerization. But when we see the crystal structure, we can see from crystal structure that there are a kind of pi-pi stacking type of interaction, and also the double bonds are very closely spaced. That means the double bonds are within 4.2 angstrom, which actually fulfill the Smith criteria, that if you have a double bond, vinylene double bond, which are closely spaced below 4.2 angstrom, and the obtuse angle is near to 90 degree, then they will undergo topochemical reaction. In fact, when you irradiate the crystals in solid state and then do the NMR, we see a peak which corresponds to this dimer, the 2+2 cycloaddition product, which is also characterized by NMR also. So we are confirmed that there are two processes happening. One is trans to cis isomerization, another is 2+2 cycloaddition reaction. And interestingly, the crystal is so elastic, and it can actually it can bend without much deforming its surface morphology. There is no change of surface morphology. Even if you see a closer look of it, I am not showing it over here, there is not a significant change of surface morphology even after bending. Coming to the mechanism for this, we must remember the mechanism of sunflower actuation. So before that, I'll show the sunflower actuation. Let me explain the mechanism over here. So when you are irradiating light from a particular face of the crystal, and we can see the photoproduct, the concentration of photoproduct in this side is more than the opposite side of the crystal. Okay, so this phase will have more photoproduct because this light cannot invade through the crystal, because this light do not have that kind of invasive power. So the phase in which it is illuminated, the photoproduct will be more than the opposite phase in which reactant concentration is more, and this creates a bimorphism, and because an interfacial strain inside the crystal, because one side has different packing, another side has different packing, and that actually creates a lot of stress within the crystal, and as a result it bends either away from the crystal or away from the light source or towards the light source. But when it will move away from the light source and when it will move towards the light source, that's the interesting part. If the reactant phase has higher cell length compared to the unreacted phase, then obviously it will move towards the light source. Okay, so we can actually correlate this one with the sunflower mechanism, with the mechanism of sunflower movement, as you have recently published this one in 2016 science paper, that there is a hormone which is called auxin, which is actually the culprit for I will not say culprit, I will say the key player for this mechanism. This auxin is photophobic, and in the side in which the sunlight is falling, the auxin actually accumulates in the opposite side and triggers the growth of the plant. And if the opposite side grows more than the side in which sunlight is falling, obviously it will bend towards the sunlight. So the same mechanism is happening in our case, as you can see from the different characterization techniques. So I will finish over here, and just a message. So just a message to the students that. So these are the different research work, the other research work that is going on. I will not go through these. These are the previous research. So the conclusion is that we are mainly inspired by different types of smart material that are present in nature, specifically the actuation in the nature and the actuation which is triggered by light. And we are designing molecule and understanding their function and manipulating their function, and then try to show some application that can be used for different purposes. So just an advice to students that just explore nature by yourself. The technology around you is really tremendous. Try to ask questions: what is happening in the nature and why it is happening. That I have shown you only a few examples, but there are many other things which is happening in the nature. Just try to explore and be curious on your part, and then go for searching, research, and all those things. Come for research if you are sufficiently interested on that part. And finally, thank you for your attention. I hope I have concluded in time, or just overshooted 1 minute or something like that.
Yeah, almost. Thank you, Manusda, for this very informative lecture. So I'll ask the audience to ask some questions. Okay, Shubhradeep, go ahead.
Hello, Mr. Dr. Manesh Panda. It's a great talk. So I'm just a little curious. Means, is there any studies was done regarding that? Means, what happens if you place those crystals under the X-rays in situ? Any in situ studies to see the real-time changes in terms of crystallinity or crystal cells or those things. I don't know if there is something, some devices are like this or any setup for this.
Obviously, we don't have that setup, and at this the system we are having here, it's not possible to do those kind of research. Now, those systems are obviously there. There are crystal, crystal diffractometer which are equipped with the UV light, UV lasers, and you can trap the transient state. But those are kind of dream to us, in at least considering the present infrastructure.
Yeah,
but those are present. Yeah.
Okay. Thank you.
Okay, due to the shortage of time, we will not take any more questions. I just one small question, Dr. Panda. This you mentioned about the actuation in crystals. So as we know that in case of these crystals, they are more robust materials. So how do you make them actuate? Means the molecules are very closely packed. So how much they have the, are they allowed to move in the solidly packed stage? Are these soft crystals or what kind of crystals? These are some different kind of crystals.
Well, that depends on the material. If you have obviously crystals are very soft. These are organic crystals or metal organic crystals are soft. These are not metal, purely metal or alloy crystals. We are working with organic crystals mainly, or metal organic crystals like metal organic complexes. So they are mainly soft. Their Young modulus is much more smaller compared to the metal crystal. But the problem is this elasticity depend on, if I understood properly, that elasticity, how much you can move. So that elasticity depends on the interaction present in the crystal. If you have proper interaction that can, break and again reform, then your elasticity and the crystal integrity, that means crystal will not break, will be much higher. But if you do not have proper interaction which can prevent you the damage of light deformation, then you will not be able to bend too much extent. So this, in the same series, we have different substituent crystal of different substituent. They do not bend up to 200 degree. They bend up to only 30 degree after it's bent. So the elasticity is also an important factor in order to achieve the extent of bending or extent of deformation induced by light.
Actually, as you told about the cooperativity, so the directionality of the movement, unidirectional movement is very important. So maybe crystals are important, but as you said, the elasticity of the crystals is also very important to get this kind of, to explore this kind of properties. So that's what was the question. So I'll just read out one more question from a student of our department, semester 3, Mr. Ponesh. He says, "Thank you, sir, for your informative lecture on bio-inspired materials. My question is regarding the time scale of the actuation. Is it matching with biological systems?"
Very good question, actually. It is faster than biological system, in fact. But it may not be robust like biological system. As soon as you irradiate, it starts moving. But biological system, as you can see, the blooming of a flower or any kind of light responsive system, sometimes very slow, depending on the requirement or depending on the species actually. So we cannot compare directly with which biological species. We have to compare with a specific biological species. So it's not a general comparison. Okay. So, but in some cases it's very fast. That depends on the light intensity also. If you have very weak intensity light, it will bend very slowly. But if you have a laser light or very high intense light, then it starts, moving instantaneously.
Okay. So thank you, Professor Panda, for such an interesting lecture. So due to the shortage of time, we'll move fast to the next lecture.
Okay. Thank you. Thank you very much. Thank you all.
Okay.
I think the next is Animes, right? It's one of my friends from CSR NEET. Okay. Welcome, Animes.
Yes. So it is my next. I would like to introduce Dr. Animesh Samanto, who is presently an assistant professor of chemistry at Shiv Nadar University, Noida, and he did his bachelor's from Vidyasagar University and MSc from IIT Madras, and later his PhD from National University of Singapore, where he worked under Professor Yante Chang. I know Professor Chang during my stay at Postec. So he's a very tough person, and being from that group, I believe he has a wonderful experience and wonderful training under him. So his research interest is in chemical biology, organic photosynthesis, and biosensing, diagnostics, etc. And he routinely published in very high impact factor journals, including JACS, Advanced Materials, etc. And his works are highly cited and highlighted by various media houses. He has also won a number of awards, including the Padmanabhan Memorial Award, IIT Madras, and Ramanujam Fellowship, DST Inspired Fellowship, and also the first Johnson & Johnson India INC Asia Outstanding Graduate Thesis Award. So these are to name a few. So today he is going to give a talk on nanoscience in healthcare research. With these words, Dr. Samanto, the floor is yours.
Thank you so much, Rahul. Let me share my slide first. Good afternoon to all of you. Am I audible and slide is visible, Rahul?
No, slide is not visible. You can share again.
Okay, just a minute.
Animesh, are you presenting from sea beach?
No, it's background. Just a minute. Is it visible now?
Yes, it is visible.
Okay. Good afternoon to all of you, and thank you, Rahul, as well as the organizing committee for giving me the opportunity, and all the previous speakers, especially Dr. Panda. He's actually Manasta. He's one of my always I inspired from him because of his high quality of research, good humanity, as well as the Rahul, who really give me the opportunity here, and especially the Ramananda College for organizing for such a beautiful one-day webinar, Raman21. So today, I will be talking about it, basically the applications of nanomaterials. You have seen a lot of different nanomaterials have been synthesized. Now I will be focusing majorly their application in healthcare research. When you talk about healthcare, majorly we think about diagnosis as well as therapeutics. When you talk about combined together, then it's a theranostics. So these few examples of theranostics I am going to discuss today. So the diagnosis, it's usually done by
Dr. Animesh, sorry to interrupt.
Yes.
Your slides are not moving. So if you have already made full screen, share that particular window.
Yes, this is actually slide. I'm on that. Can you see slide number 2?
Animesh, please put it on slideshow.
It is probably in his computer, it is slideshow, but you have to so make slideshow and then alt tab and go to your Chrome or tab and then share that particular full window.
Oh, it's already, I'm so sorry. Let me. Let me just, I stop here and then I go it again. I'm so sorry for this interruption. Is my slide visible now?
Yes, please put it on slideshow.
Is it? Can you see the next slide?
Yes. Is it fine to others?
Yeah, I think it is fine now.
Yeah. Okay. Please go ahead.
So I was mentioning about, I'll be majorly discussing about diagnosis as well as therapeutic. When we talk about diagnosis, it's either could be in vitro or in vivo. I'll give you some example and that time it would be much clear. And therapeutics, we learn about different drug molecule. Instead of drug, can you use these nanomaterials for therapeutic purpose? So that kind of few example I'll be giving today. So when we talk about in the introductions, that nanoscience is a convergence of physics, material science, and biology. And this is the manipulations of a materials atomic or molecular level that is the extremely small. What Dr. Chhatra has very beautifully explained the basic part of nanoscience. And here I'll be majorly discussing about the applications. And as you know, this application recently 2020 got Padma Shri award because of the development of a nanomembrane which can remove the arsenic, which was Professor Ghosh mentioned, which is a major problem in Malda district. So that's how we can really understand the applications of nanomaterials is a huge demand in today. So now, as it is already discussed, I will just briefly talk about that nanomaterials, which is 1 to 100 nanometer in size. So these are the different example of organic or inorganic nanomaterials, which previously some of the speakers have already discussed about it. So these organic nanoparticles or inorganic nanoparticles, both the nanoparticles have been extensively used in different applications, but my focus will be majorly on the healthcare research. So this, when we talk about this type of nanoparticle, Dr. Chhatra has nicely explained about the top-down approach as well as the bottom-up approach. So here, basically being a chemist, we wanted to always go for the bottom-up approach using a simple salt of inorganic salt, and then we do some reduction oxidation by which we could reach to the nanoparticle level. Each process has some advantages and disadvantages. However, depending on how we synthesize this nanoparticle, their optical property can be changed. Their size can be modulated, their shape can be modulated. It either could be organic or it could be inorganic nanomaterials. For example, here, when we change the size of the nanoparticle, the optical property is shape shifting. Similarly, when we change the aspect ratio of nanoparticle, we can change the optical property. So not only optical property, like iron-based nanoparticle, we can change the magnetic property, and all are at the nano levels. So now we wanted to use this type of optical, magnetic, electrical property for different application, and this application today my major focus will be in the healthcare research. Now, when you talk about this nanoparticle as a bare nanoparticle, always question about toxicity. What Dr. Chhatra nicely mentioned, like we need to do some passive method by which the nanoparticle can be coated. When we coat the nanoparticle, the nanoparticle becomes biocompatible. This coating material usually use different kind of polymer like a polyethylene glycol, or even simple like a DNA or protein, which is known to be a biopolymer. So then this toxic bare nanoparticle, we can able to make them as a biocompatible nanoparticle. However, these nanomaterials can carry their own optical, magnetic or electrical property. So then this surface, when it is modified, being an organic chemist, whenever we have a different functional group, we can modify that functional group whatever we require. If we wanted to do drug delivery, we can load the drug. If we wanted to target to different cancer cell or different disease cells, we can target to different antibody or different bioconjugate polymer. So by which we can do the targeted delivery as well as therapeutic applications. So that's why we can do have a lot of applications of nanoparticles. However, today's major application I'm going to talk about healthcare, biomedical research, cancer delivery, and so on. So when, as I mentioned, like a diagnosis, we can think about two different type of diagnosis. One is in vitro diagnosis, where the body fluids like blood sample can be collected, urine sample collected, or else. In that kind of cases, we can do like a one simple example here is given. Here, like this is a simple device. It's a lateral flow assay method. Here, HIV positive blood sample having P24 antigens. So we can drop the blood sample. When it passes through it, one is the control, another is the test. So if this test part showing this color, which giving the information of a positive HIV. And when we talk about something not color sample, like a urine, saliva, plasma, like what we mentioned recently, breakthrough of corona, we have done a lot of diagnosis by using antibody-based method. In this case, nanoparticle also play a key role. In that kind of cases, as RNA virus are not having any color, so we usually use secondary antibody attached with the gold nanoparticle. And gold nanoparticle having optical property, so depending on the optical property, it can give a color, and this color will come to the test drive. So by which, if it is color, can say it's a positive, if it is not color, it is a negative. Now the question about when it is in vitro, everything we may not able to do all the diagnosis by using simple urine or blood sample. For example, let's say something inside the body, something like a liver has got damage. So that's called liver cirrhosis. How can you detect this liver cirrhosis? By using this kind of nanoparticle as our tool. So in that kind of cases, we need to do some preclinical study. For that purpose, we need to help. We need a help from the different animal, like a small mouse to rabbit to even big animal model. Further, it can convert to a clinical purpose. It usually takes a long process. So one example of here, I'm going to talk about like liver cirrhosis, how we could able to detect by using nanoparticle based diagnostic probe. So usually liver cirrhosis, what happened? Like whenever we suffered in fever or during that time, headache also, usually we take a paracetamol, which is a well-known drug to all of us. And this paracetamol, doctor recommend 650 milligram for adult, 8 hours interval. Sometimes maybe in the village, the patient does not know which one is the paracetamol. So they may take it mistakenly more than what is recommended. So what should be happen? During that time, side effect could be a liver cirrhosis. In addition to that, if you drink or consume excess of alcohol can be cause for liver cirrhosis. Using a simple 1 nano probe, here some nanoparticle which conjugated with organic dye. The nanoparticle is emissive, organic particle is absorbed that emission at the very beginning, but because of this excess of paracetamol, which gives a byproduct as a peroxynityl, which breaks this bond where this dye organic molecule can be removed, and this can be a fluorescence or luminescence. By using this concept, now we have studied preclinical model where the animal, so this nanoparticle has a tendency to goes to the liver. So first it confirm it is going to the liver or not. After confirming, then this nanoparticle composite initially does not show any color because it is non-toxic on that time. However, When treatment with 250 milligram per kg of paracetamol, it's increasing with time the intensity, which indicating liver is getting damaged more and more with time. So which was quantified depending on the amount of paracetamol, it get damage the liver more and more. So by using this simple nanoprobe development, we could able to do the diagnosis of a liver problem or not. So not only like this type of example, there are many research currently ongoing. So it has been extensively used different consumer products. I'll be giving few examples for your curiosity to get interest about nanoparticle research. In addition to that, there are a lot of applications, different diseases. Especially I will talk about cancer, because if you see the major application of nanomaterials in cancer research. Why does it so? The reason is the cancer and blood, when we see the blood vessel, the normal blood vessel does not have any leaky nature. But the cancer cell, cancer tumor having the blood vessel is leaky nature, and this leakage is perfectly matching with the nanoparticle size, what we mentioned about 1 to 100 nanometer. So that's why this nanoparticle easily can go inside and without damaging or defecting to the normal tissue, it can go to the tumor tissue. That's the reason actually nanoparticle can be useful tool considering for drug delivery or diagnostic or therapeutic purpose. So that's the reason actually the cancer. So obviously like why the cancer research is very important, that's most probably all of you know, because cancer is the cause of 12% of all death whole world. In India, almost 1.5 to 2 million estimated cancer cases are there. But treatment of this cancer, basically we need to develop a drug. That drug has to be approved by the FDA. So to do this also, it takes around 13 to 15 or sometimes 20 years in average. That's why early diagnosis is the most important. So if cancer cases are detected at late stage and if you treat with the drugs, there is not much effective. That's why we need to detect at early as possible. And in that kind of cases, this extremely small, tiny nanoparticle, which has a better tendency to go to the tumor area, that can be useful for a better diagnostic materials. So far there are already available some technologies which currently used in clinics. Among them, biopsy, endoscopy, pap smear, and recently this is developed on in vitro base is the CTC isolation, circulating tumor cell isolations. But in these particular cases, obviously it is a painful, so some drawbacks are there. To overcome this drawback, actually there are nanoparticles play the major roles. So these nanoparticles having both advantages. One advantage is the passive targeting, another advantage is active targeting. What the passive targeting means? Because the nanoparticle directly can selectively goes to the tumor because of the size effect and leaky vascular nature of tumor. And active targeting, what is it? That basically you can conjugate it with your targeted ligands. That can be an antibody, what Dr. Shatra also mentioned about it. So now, when you conjugate this antibody, then the antigen overexpressed in the cancer cell, depending on what type of cancer, their expressions of antigens could be different, and complementary antibody, at least 372 number of antibodies already available, so which can be conjugated and can target to the right locations. So that's the reason nanoparticles have been extensively used for research. So yes.
Animeshka, just click on the hide. It is blocking.
Okay.
Pop up.
Thank you so much.
Thank you.
So today's webinar is Raman 2021. So here recent advances in materials and nanoscience, but today I will introduce another Raman which was introduced by C.V. Raman, who is the Nobel laureate from our India. So he discovered a Raman spectroscopy, and here I will use one of the optical property of Raman, which signal was very weak. That's why although it was discovered in 1928, still it was not flourished. But recently, by using this nanoparticle, and if we have a Raman active molecule, then what happened? The Raman intensity can be enhanced. That's called surface enhanced Raman scattering. Now, this nanoparticle we are using, which can target to the tumor in a passive or active way, and then this Raman reporter is there, which was initially was not active because of the signal intensity was weak. Now signal intensity is strong, so then we can get the better sensitivity. Now we conjugated with the BSA protein to make it as a site biocompatible. Toxicity will be very, very less. Now conjugated with the secondary antibody. This antibody actually can target to the specific tumor cells where having the antigens. By using this also we could able to detect what type of tumor is. So initially by scanning where the simple skin does not have any color, its color representing there is a tumor which is from this nanoparticle having the surface enhanced Raman scattering property. So when we do diagnosis, obvious question is what is the solution? What is the therapeutic of this cancer? Usually the therapeutic is the surgery. There is a chemotherapy, but in this kind of cases also nanoparticle play major roles. I will give you a few examples. But in this kind of surgery and chemotherapy, whatever the traditionally used, it has a lot of side effect that most probably all of you know. Now the question is, can we change this chemotherapy drug without medicine? Cancer can be treated. So that is the new era of research, and I will give you few examples how it can be done by using nanoparticle for therapeutic applications. Because of the shortage of time, I'm not able to go to the mechanistic understanding, but few examples can definitely will give you idea. So now let's see how nanoparticles can play for the surgery as well as the chemotherapy. So like this particular mouse having tumor here, if we see in the simple daylight, it might not be visible, but because of having nanoparticle and targeted, that's why we could visualize them. By zooming, we can see even the big tumor which can surgery can be done, and then this one is not possible to visualize. So this is the actually why happened now, because just Dr. Shatra has mentioned different quantum dot. It's not only quantum dot, there are different nanoparticle can be developed which can actually go to the tumor location more effectively than the normal because of this leaky vascular nature, and because they are optically active, then you can directly see them. So by which we can use nanoparticle as a good surgical platform. Next, in these kind of cases, actually we need to think about what type of nanoparticle, what are the size, shape, does matter. And here is showing like when you pegylated means what type of coating is there, depending on that accumulation will be differ. If it is very small, it can goes to the kidney and other organelles. Otherwise, it can be tuned to right locations. Similarly, with respect to smaller and the larger particle. So that's a lot of research ongoing. So depending on the size, depending on the shape, depending on the aspect ratio, the tumor accumulation will be more, and which can be controlled with respect to the other organelles. Here, the chemotherapy, just when the Professor Ghosh was mentioning, probably one of the students was asking like how this kind of nanoparticles, if it is not water soluble, how it can be useful. So as we mentioned that nanoparticle can be modified by coating, and here different drug is already developed. However, the all drug may not be soluble in the water. If it is not soluble, you can formulate it with nanoparticles, and this nanoparticle is so small, it will be almost like a transparent when it is given like a saline sample. Directly the way chemotherapy drug can be treated. So by which we could develop a drug carrier which can goes to the right locations. So in not only diagnosis or therapeutic by using this chemotherapy drug, without any drug, directly we can use some mechanistic effect like a gold nanoparticle. So this nanoparticle obviously will go more tendency towards the tumor locations, and when it is reached to the tumor, basically this nanoparticle can be made in a different way. So this nanoparticle, they make as like a disc. If you can see this disc, the side is the edge is very thick and sharp. Now this particular disc should be in a nano level, and when this disc reach to the cell, now if you apply the magnetic field, okay, if you apply the magnetic field, basically it will start to, yes. Just try to see when we apply the magnetic field, basically it starts vibrating. Because of the vibration, then the different kind of biomolecules will be damaged, as well as the cell membrane can be damaged, cause for the death of the cell or recovery of the tumor. Similarly, another example like a nanoparticle, where the gold nanoparticle which can cause for the temperature enhancement within the body when lasers are treated. And as you know, DNA have a melting point. They are double helical structure, but if increase the temperature, it will open up. So the room temperature drug can be loaded within the DNA, and when we increase the temperature, then basically drug can be released. And yes,
5 minutes.
Yes, sure. 5 minutes is good enough for me. Thank you so much, Rahul. So by using this concept, we can do both as well as therapeutics. So these are the different applications of theranostics. But still, if we think about this should be in clinic, it will take another 15 to 20 years. That only is the scientist has proposed. So not only like this kind of diagnosis and therapeutic, day-to-day life, different consumer product, home remedies also use different nanoparticles. For example, deodorant having silver nanoparticle, which kills the bacteria. That's why the smell can be removed. Similarly, zinc nanoparticle are there for killing the dead and cleaning the dead cells from the skin. Titanium oxide nanoparticle in the toothpaste, which helps to brightening the teeth. So these are the different commercial product and different company they already have developed, and majorly cases when we go out, we use different sunscreen having different nanoparticles, and these nanoparticles actually protect from the UV. That's why our skin can be protected. So that's why there is a huge applications of different nanoparticles, and that's the great opportunity for research in advanced materials for many applications. I just gave you some glimpse of different applications. So if you still, those are undergrad or masters thinking about to do advanced research, looking for opportunity, Obviously, there are a lot of fellowship, as well as I welcome to our university, where also we do offer similarly with advanced research facility with MSc research, where our major focus is on research with 12,000 fellowship, as well as the PhD with 50,000 fellowship. So it's going through like some application followed by interview. At last, it's an acknowledgement. I'm very much thankful to Ramananda College and especially few person, Chairperson Dr. Shapna Ghurai, Coordinator Muhammad Ali Khan, HOD Dr. Ajay Kumar Manna, Convener. Lot of, especially I will give thanks to Rahul, who is my like a beloved brother, as well as the all organizing committee members and all participants and students for their valuable time for listening. And I also thanks to SARP for giving some grants and Signother University and Signother Foundations and my students. Thank you so much for listening, and I will be extremely happy. I expect maybe more questions. However, if I cannot give any answer, that's my contact number. I will definitely respond if you reply. Thank you so much listening. Thanks.
Okay, thank you, Animezda, for such a wonderful lecture. So we'll take a couple of questions, maybe very quick ones. Anyone in the audience interested to ask a question? Okay, one from Joydev. He's a third semester student from our college. Joydev, go ahead quickly.
First of all, I would to say thank you, sir, for your informative lecture, sir. Can you comment on the excretion of the nanoparticle and it is possible to excrete them using our kidney?
Yes, very good questions. Obviously, the nanoparticle excretion usually happen depending on the size of the nanoparticle. If it is less than 5 nanometer, automatically it goes through the kidney and it can goes through the urine sample. That's the reason actually small organic molecule, they do not stay for longer time inside the body, which usually comes out through the urine. But in case of like a bigger nanoparticle, so it's supposed to go through metabolic process and by which it's supposed to be excreted. But depending on the size, it may stay from body for longer time also. That's the reason actually it still takes some more time to have the most biocompatible nanoparticle to come up to the clinic. Thank you.
Okay, thank you, Dr. Shamanto. I think there are no more questions right now, but as Dr. Shamanto mentioned, you can always get in contact with him to ask any questions or queries about this talk. Okay, so we'll move to the next presentation, and I invite Subhrodip to introduce the next speaker. Subhrodip, over to you.
Thank you, Rahul. Now the next speaker is Dr. Shamrat Ghosh. I welcome Dr. Shamrat Ghosh, who would be the final speaker for this webinar Raman21. Before he starts, a small introduction I will provide about him. Dr. Shamrat completed his PhD in 2018 from CSIR NIST, Kerala, under the supervision of Professor Ajay Ghosh. He is the recipient of 2 highly prestigious postdoctoral fellowships, which are JSPS and Alexander von Humboldt. First, he joined Professor Seki's lab with the JSPS fellowship in 2019. Later, he joined Professor Arne Thomas Group as a Humboldt postdoctoral fellow in 2020. Currently, he is working as a scientist at the Central Leather Research Institute, Chennai. His area of research interest is engineering porous frameworks and multidimensional applications, functional semiconductors for optoelectronics, and energy harvest and storage and development of smart chemicals for leathers. The title of his talk is NIR Photography, Seeing the Unseen Through the Lens of Supramolecular Nanocomposite. Okay, Samrat, now you can go ahead.
Yeah, thank you for the introduction, Dr. Subhrodip. I thank all the organizers for giving me opportunity. Am I audible clearly? Is there internet issues?
Yes, Samrat, you can go ahead.
So I'll share the slides also, just entire screen. Is it possible? Can you see my slides?
Not
Yes.
yet.
Not yet. Just a minute. So I put entered
I think Onimus Samantu sir has not switched off his presentation. That slide is still
Stop
being
presentation.
there.
No, I can share.
Yeah, now it is stopped. I think now Dr. Samrat goes.
Yes, yes.
Now you can.
Yeah.
Now you can redo the thing.
Okay. Might not screen record permission system preference go
And
to
now I
issue
think
system.
try to say it will.
Is it now my slides are visible?
No, not yet.
Not yet.
There is an
can you
option
just
at the bottom of your screen which shows like present now. There is
arrow?
like
Present now. Yes.
Present
click
now.
That one.
And go to your entire screen.
Upside arrow in a rectangle.
Upside. Just a minute. It's sometimes Google has present now. It's share entire screen and entire screen only my
Yeah, you just then need to.
showing.
Then a pop-up will come up, and then you select the screen and share. Click
Share
OK.
screen and share.
Yeah, put share.
It's showing something is
okay. Can you
problem in system
okay,
preference.
can you just leave and then join again? Can
Just
you just leave and join again?
Yeah, I'll try. Just sorry, I'm sorry for this.
It's okay.
No problem. Okay, I got it. I got the issue.
Is it because of the security reason we're recording?
Yeah.
Yeah.
Okay. We have a slide for this kind of situation.
I think Samrat is trying to join with another login ID. Probably we'll wait.
Yeah, Samrat is online again.
Yes, it was visible just a minute before.
Okay. Your mic is not on.
Turn on your mic, Samrat.
Samrat, turn on your microphone at the bottom.
Okay, I got it.
Okay.
Hello.
Yeah.
Yes,
it's
yes,
okay.
we can hear. I think your presentation is loading. I think.
Hello, can you hear me?
Now it's fine. Yes.
We can see and we can hear. Okay, go ahead.
Samrat, I think you are mute. You are not audible. I think you are mute. You are not audible, I think.
Is it now also audible?
Yes, yes. Now it's fine.
Yeah.
Now it's
Now,
fine.
now the sound is okay?
Sound is fine.
And the screen, can you
Yes, we
see
can
it?
see the slides. Yes.
Yeah, full screen?
Yes, yes. Everything is
Perfect.
fine. Just go ahead.
Perfect. Yeah. Thank you so much for inviting me for the this talk. So I thank Dr. Shubhradeep, who is my very good friend, and Dr. Rahul is also my very good friend and my senior to my laboratory. Also, I thank Dr. Samashish and all the speakers for giving a wonderful talk. And today, I'm the last speaker, but all the other speaker has set the base for my talk. So they have given all the basic knowledge which is required to listen this talk. So this talk will be mainly focusing on the NIR photography. So in this one, we'll be not doing much of chemistry. We'll be doing some photography. So student might be interested, but I'll be talking small chemistry in between. So it's entitled as NIR photography, seeing the unseen through the lens of supramolecular nanocomposite. I first thank the whole organizing committee for organizing such a platform to share our research experience. So first I'll explain what is my research interest. My basic research interest belongs to the functional organic semiconductors. Why I want to mention that organic semiconductor? Because nowadays we want to do something like flexible devices. Like you want your smartphone to be flexible, or if you want to build a solar cell, it should be foldable solar cell. Present solar cells are not flexible. So you can fold it, and whenever you want it, you can use it. So for flexible devices, we do not require the single crystalline silicon or inorganic semiconductor. We require something which can be foldable and which can be put it into different shapes with very thin layer of very thin active layer. Here you can see, I'll use my laser pointer. So here you can see the basic fundamentals of this kind of semiconductor, where we just excite the semiconductor. So basics of the semiconductor has been explained by Dr. Shatra. He has explained all the things, so this is easy for me. So when you shine with light, the electron goes up. Now this electron and hole is separated. You can recombine it. You can get emission. You can use this electron. You can get hydrogen because it can reduce the water into the hydrogen. And if you externally connect this electron and hole, then you can get a solar cell. So this is the basic, and this basic fundamental is very important to design a high performance device. Now this semiconductor need to be chemically engineered or molecularly engineered. So I do some molecular engineering where we use some basic pi conjugated system, which is, you can see benzene and benzene just connected to the CC bond, or it's a fuse system, or different kind of, it's a kind of a donor, acceptor and donor kind of system. And this system can be used as a supramolecular polymer, where this molecule can self-assemble. What is self-assembly for the students has been explained by initial talk by Dr. Dash, and also Professor Ghosh also explained that what is the supramolecular self-assembly. And then also we can fabricate into the framework structure, which is I named as covalent. It is known as covalent organic framework. This is also introduced by Dr. Ghosh, so I will not go into the details. Now, this kind of semiconductor can be used for several applications, like photocatalytic water splitting, dye-sensitized solar cell, or several other things. Today, as I mentioned, that I'll be talking on the NIR photography. So before going to the NIR photography, I'll be talking about the spectrum, which is electromagnetic spectrum, having different wavelengths of light, from the radio, microwave, infrared, visible, UV, X-ray, and gamma ray. And each of the wavelength has been used for certain technique or for certain imaging technique. Like if you use the radio wave, we use this radio wave in NMR. You all know about the NMR, nuclear magnetic resonance. And this radio wave exactly excites the spins from one state to other, and you detect the spin in presence of magnetic field. If you excite with the radio wave, you can create the energy difference, and then you can use it for detection. So MRI is such a one technique. Then microwave, if you use, then you use in the EPR, electron paramagnetic resonance. So where you see the electron spin. Instead, in NMR, we see nuclear spin, or in EPR, we see electron spin, and it can be used for several non-destructive methods, such as here shown for measuring the paint thickness. And there are several other techniques like FTIR, infrared light has been used for the FTIR, and also it can be used for the thermal imaging. So presently, thermal imaging is a very important technique because of the COVID situation. So they can easily scan a large number of population who has the high temperature, and they can sort out who has the high temperature things. Visible light, we all know, we see by our eyes. UV light is another useful light which can be used to detect your fingerprint. If you do some crime, after the crime scene, the UV light can be used for detecting the fingerprint. Also, the X-ray is one of the most widely used wavelength light, which electromagnetic spectrum, which can be used to detect structure of a molecule. Like if you form a single crystal, the structure can be solved by the X-ray. Not only in the molecular scale, in the macroscopic scale also it has immense application. We all know why X-ray is needed, and this picture especially is very unique because this is the first X-ray picture taken by Röntgen. And also there are gamma wave, and this wave can be also used for the some biological application and several other applications. In this all spectrum is very useful, and today's talk will be mainly looking at the near infrared, which comes between the infrared and the visible region. It is longer wavelength than the visible, but little bit lower wavelength than infrared. Now we know, we have seen by Dr. Panda's talk and also by Dr. Das talk that how we see the things, that visible light, why we can see it. Now we cannot see the infrared light. Now how we can see that one and how we can use it, that will be our talk. And today's talk mainly will be playing with the molecule to create a filter. So we'll be making a filter which can be used for the near infrared photography. So let's see what is near infrared photography. Near infrared photography, you can see two images. This is taken by the Hubble Space Telescope. You know Hubble Space Telescope, it's launched in 90s, and it used to see the astronomical events. But this Hubble Space Telescope, mainly it is based on the visible light. Near infrared light has been used a bit only. By the way, in between I'll tell that am I audible or not. Am I audible?
Yeah, audible. Okay.
Yeah, great.
Yes, sir.
So this is the visible light taken photograph. Now, if you see this same photograph with the near infrared camera, you can see lot of more information, lot of new galaxies. Now, visible light, you can see dust, a lot of dust here. In near infrared, it is almost not there. So, as we know from the Rayleigh scattering, this is the BSc basic knowledge, where the intensity of light is proportional to the wavelength, inversely proportional to the lambda to the power 4 almost. So the wavelength of light is shorter, means that will be scattered more. If wavelength of light is longer, it will be going through. So compared to visible light, if we do see with the infrared light, we can get much lot of information which was missing in the visible light. Now let's talk about the origin of this universe. So today's talk, Dr. Dibyendu Das has mentioned that our first life has been created in the earth in almost 3.8 billion years before, and our universe is almost 13.8 billion years before. So first 10 billion years it took to form the first life. So you can understand how our life will be complex. So nature took this much of time. Now after the Big Bang, there was a dark age. Can anybody imagine Big Bang was for how much time? It happened in a fraction of second, very much 10 to the power minus 4 as much I remember. So that much fast it happened. And then after that, a dark age was there, and then hydrogen generation was there, and reorganization, and then the formation of galaxies was there. So when the galaxies and the elements and other materials start forming, they start emitting the UV lights. Why we should see in the NIR photography is that to understand that, we need to understand one phenomena called redshift. So when a galaxy forms that emits UV light, but that has to travel from here to here, and when it is traveling this light, the wavelength gets stretched. So this is called redshift. So if the galaxy is going away from us, so then we see the if the galaxy, sorry, here the direction is wrong. If the galaxy is approaching towards us, we should see the shorter wavelength. But if the galaxy is going away from us, please ignore these arrows. So if the galaxy is going away from us, we should see in the stretching in the wavelength. Means if the wavelength was UV light, now it's stretched to the near infrared light. So that is the reason why we should see, we should send a space telescope which can observe this event through its near infrared camera. And to observe these events, NASA is sending its still now the largest project, which is called James Webb Space Telescope. And in this James Webb Space Telescope, there is a near infrared camera in the heart of this telescope. Almost this is a $10 billion project, and in they still are not able to launch it. The launch is getting delayed and delayed because it's a highly complex thing to do. So our main interest is the near infrared camera. Now, how we can make near infrared camera? So before going to that, we should not only the application in the space program, this also has application in this real world. Like if you have 1,000 acres of land, how will you monitor the plants are growing in one section in a proper way and another section in not in a proper way? To detect that, we can use the NIR photography. So plant is a excellent molecule, excellent system which can reflect the IR light. So all you have experienced that when you just feeling very hot and go down to a plant, you feel a bit colder than the other place. This is nothing but because plant reflects NIR light very efficiently than other buildings or something. So this is why we feel cold. So if the plant leaves are very healthy, it can reflect the maximum NIR light, whereas if it is the leaves are dead or stressed, there is less amount of NIR light. So if you monitor from a satellite or by sending a drone kind of thing for a large agricultural field, you can clearly image which portion of your field is growing properly, the crops are growing properly, which field not. Not only for the vegetation, maintaining the food quality, like if you want to know your vegetable is fresh or damaged, for forensic applications. So suppose somebody has killed someone by wearing a dark cloth, and in that dark cloth some blood stain is there, but we cannot see the blood stain on the dark cloth because both are darker in color. So we can use the near infrared photography to see the blood stain over there for night vision, and also for the healthcare application, like finding the veins. So when we are going for a blood donation, sometimes finding the veins is difficult, but this near infrared photography can be used for that. Now, how to make that near infrared camera? So we all have the camera and we do the photograph, we take the photograph, but we never open our camera. So if we open our camera, we can notice there is a near infrared reflecting filter, because the detector till now we are using kind of CMOS detector, which is sensitive from the visible wavelength to near infrared wavelength, almost up to 1600 nanometer. So because the present ambient condition has a lot of near infrared light, so that can give a not a clear picture of the visible light. So that's why we use a near infrared reflecting filter, which gives us a clear visible image. So one can cleverly design, if I make a filter which can pass only the NIR light and stop the visible light, then I can see the near infrared photography. So yeah, it's that simple. So just we need to make a filter which can pass the NIR light but completely stops the visible light, just opposite to the previous one what we see for the visible light camera. Remember that during that time you should remove the near infrared filter, reflecting filter from the inside. Now our challenge today to make a near infrared filter which can absorb all the visible light and pass the near infrared light. So commonly we see the inorganic materials has been used for this making of near infrared filter, but today we'll be trying to make a organic near infrared filter. Because organic, why I told? Because it gives the flexibility. So I can make a flexible filter. If I feel my filter drops somewhere, it won't break, and it can be foldable or moldable in different shape, and it requires very low cost and low room temperature synthetic condition. So that will be preferential. So here we aim to prepare flexible near infrared optical filter. Now to make a optical filter, now to cut off the visible light, we need to use something called dye. You know the color. Why we see color? Because it absorbs some part of the light and doesn't absorb some part of the light. That is why we see the color. Now when some material is totally black, that means it absorbs all the visible light. That's why the color is black. Now here are the some of the dyes which I showed in this slide. This is the one of the first synthetic dye, and can anybody guess who has synthesized this dye? It's done by Professor Parkin. In 1800 something, he has prepared this dye, and this was the first synthetic dye which commercially used for the dyeing of the clothes. There is another dye, it's called indigo. It's a natural dye and also can be synthesized. And Bengal has a long history of indigo. So we all know about Nil Vidroho and why it happened, and then how French chemists came up with the isartine synthesis and the synthesis of indigo. And then this is another naturally occurring dye, porphyrin, and this is another synthetically dye, perylene diamide. Today I will not take this dyes. I will take another new dye which is called diketopyrolepyrrole, and this dye is very fascinating dye because this can be synthesized in one step, and in a large production is possible. And I think all of you know this car. It's called Ferrari, and this car has a color, red color, and this red color comes from this dye. So that's why this dye also known as Ferrari red dye for the Ferrari red dye, its name. And also it has a bright color and fluorescence spectra which can be used for several applications, and good semiconducting property which can be used for the solar cell, and because of this fluorescence can be used for the bioimaging purpose. But today we'll be mostly sticking on the color of this dye. Now we aim to create black material can be created by mixing several dyes. We know when we play Holi, there are several kind of colors are there, but if you mix all the color together, we can create the black color. But can we create a black dye from a single component system? So that I will be explaining here. So this system, if you look carefully, is here NH bond is there, here CO bond is there, which can hydrogen bond and form an assembly. And in this direction, you can extend the conjugation, and the perpendicular direction, you can do the pi stacking. So these are our advantages to use this dye to create one single component dye for the creation of black dye. So there I will be using a technique called molecular aggregation. Now this molecule, if you consider just like this one, so this is the monomer state, it can absorb here. If it is forming like this, one top of other, the absorption spectra shifts to the left, means some kind of blue shift we say. But if it is forming like this slip stack, it gives a red shift in the absorption spectra. So if we get all these three together, exactly we can cover the broad absorption spectra. So that's the concept I used for making such dye. So now here is an example. You can see which dye I showed in the previous slide. This one, when from H type, it is a red in color, but when it is from a J type dye, it is in green in color. So you can see clearly by molecular aggregation from a single component, you can tune the color just by how they will aggregate, like this or like in slip fashion. So how the supramolecular things aggregate, that I will show in this one. Is the video? The video is just a minute. Can you all see the video? Hello?
Yes.
Yeah. So in this video, you can see how the molecules form a assembly. So today you have heard of several times the assembly or supramolecular chemistry. This is just in a nutshell that how a molecule polymerize into a supramolecular polymer, which we are using for different applications. So this is the video explains that how one molecule in a solution start interacting with the next molecule and forming assemblies. So just for understanding, I'm playing the video again. So it form and it keep growing. Now with this technique that, so one is the increasing conjugation. So previously I showed that either we can increase the, either we can increase the conjugation to get the broad absorption, or we can increase the aggregation. Now we use a, with this aim, we prepared a molecule where we have increased the conjugation and also include some group like amide bond, which can help to aggregate through amide and pi stacking. So here you can see some of the photograph of this dye. When it is in the small molecule, you can see this is the smaller version. It from a orange color. If you just keep on increasing the conjugation, it turns its color from orange to red to blue to green. And if you aggregate, this is the green dye structure. This is the chemical structure of that green dye. And if you aggregate, you can get the black dye. So we are successful in the making of the black dye. Also, this molecule from gel. Gel is nothing but when the supramolecular polymer form, these are the one-dimensional network which can trap the solvents in its matrix and it forms gel. So in monomer solution, you can see it's green in color, but when it aggregates, means supramolecular chemistry also playing. So conjugation is one option, and second option is the aggregation, which gives this black color. And here you can see the absorption spectra, where the monomer is here. As I mentioned that upon aggregation, if there is a blue shift, that means H type aggregate. If there is red shift, there is J type aggregate. In our case, both are existing. So we are able to cover almost whole of the visible light spectrum. So from 400 to 700, completely we have covered. Now let's see these structures, how it looks. So I showed the video where you can see the formation of fibers. Exactly, if you see under the electron microscopy, like scanning electron microscopy, you can see this fiber for big thick fibers are there. And if you want to see in very dilute condition, you can do the atomic force microscopy, where you can see these fibers are very, very thin. Regarding the dimension, Dr. Shatra has explained how we are how these dimensions are. So you can imagine how these fibers will be. That's why their diameters are in the nanometer regime. So that's why we call them as nanofibers. Now, what we can do is that we can include these dye aggregates into a matrix and create a flexible optical filter. So as a matrix, we have taken PDMs, which
Samrat, 5 minutes.
Yeah, sure. So we can we have a PDMS, and in the PDMS, it's a silicon elastomer. If we just include the dye, we can see the color is changing and it is turning black. And if we put the complete 0.158%, means very tiny amount of dye, it turned totally dark. So this is the making procedure. So you can make at your home. There is no problem. Just buy these chemicals and put it. It can be prepared, and different thickness can be made. We have characterized them with the optical properties that it is completely absorbing the visible light and transmitting the NIR light. So our filter is ready for the application. So what we did, this is our filter we have made. We have fixed in front of a camera, which we have removed initially the near infrared filtering reflecting thing. Now we like to see this photograph. So here you can see N is blue in color, I is green in color, and R is in the red. And this is the near infrared reflecting filter, and this is near infrared transmitting filter. Now here you cannot see what is written behind this one, this black thing. But if you see with this camera, you can clearly see what was written. It was written black. So this camera can see what you cannot see by normal eyes. Let's use another example. So in normally we see the trees are green in color. Initially I have told the trees can reflect the NIR light in maximum compared to any other thing. So here you can see they are snowy white. It is just a pseudo color because NIR light we cannot see, but they reflect maximum NIR light. That's why the it is showing very bright in color. Now we can use this technique for anti-counterfeiting. Like suppose there is a barcode which is a original company's barcode, but there can some forgery can happen. They can create another barcode. So here we create a hidden barcode which you cannot see now. But if you see under this camera, you can see it. And this barcode is designed by two ink, where one ink made use for the making of barcode, and the second ink use which can transmit the near infrared light, and we can get the information of the barcode by using the NIR camera. Not only the seeing the barcode, we can read it. So if some company is a high value company want to use their barcode as a hidden barcode, we can use it, and by using NIR camera we can see and we can read it. And there is another application you can see, it's a 4,000 rupees check. But if you see a near infrared camera, you can see it is a 1,000 rupees one. Exactly, someone has wrote 4 in front of 1,000 using another black ink, but those two black inks are not from the same company, so they have different near infrared transmitting property. So that's why we can see that who has done forgery with our checks. Also, as I mentioned, if somebody murders somebody and the blood stain remains in their dark cloth, which cannot be visible by normal images, but can be visible by the near infrared camera. Also, night surveillance can be done. So here in dark we cannot see anything. So this is a kind of night vision. Then another interesting thing is that your daily use, like is this apple is good or is this spinach is good. In Bengal, one thing is that to keep the spinach very fresh, they put it into the copper sulfate solution, or they mix the brick powder with the chili powder. Now, how will you quantify that? Now, if you see under the near infrared camera, you can see this apple is not very fresh. There is something, because near infrared has longer wavelength, so it can get information from the inside. And here also you can see this is fresh, but this is soaked in the copper sulfate, so that's why black stains are there. And here also you can see which is the original chili powder, which is the original turmeric powder, and which is the adulterated one. So in summary, we have created a molecule which can form assembly, and because of this assembly formation, we can get the black color which can be used for the hidden barcodes. I'll go into the another thing for just a minute and then I'll finish it. So here I'll tell about the covalent organic frameworks. For morning onwards, you have heard of the metal organic framework, and Dr. Ghosh has explained what is metal organic framework as well as covalent organic framework. I'll tell in short that it is just 1 or 2 or 3 dimensional polymer linked with the covalent bond instead of metal bond. If it is metal linked, then it's a metal organic framework. This is the covalent organic framework. So you can synthesize very easily. You just take amine and aldehyde, and you know this is a condensation reaction and form a sheet base, and you can get this kind of structure which stack in this way, and you can get lot of pore structure. This has also a lot of application. Dr. Ghosh has mentioned all the applications of MOF, and similarly COPS has been used for all these applications. Mainly I'm in my group, currently I'm looking in the use of this COP as a semiconductor and for photocatalytic hydrogen evolution. So we know the importance of renewable energy, why we need renewable energy. And one of the most important source of renewable energy is hydrogen. So we need to generate hydrogen, and hydrogen can be generated from the water and in presence of sunlight. So we have plenty of water and we have plenty of sunlight. So we can use a catalyst and create such thing using the fuel cell, which already explained in the morning. And this is the semiconductor where I'm not going to the mechanism and details. So that's why I am interested in the porous organic semiconductor. So this is my laboratory website. You can visit it if you are interested, and you can get some information of this kind of porous material. So here I have created some porous material, and this material shows different color, and you can see it can produce lot of hydrogen in presence of sunlight. So this was some of my previous work, and I acknowledge all my collaborators for this many years help, so I can present the today's research in front of you, and also the postdoctoral postdoctoral fellowships and doctoral fellowships over here, and funding agencies for generously support my research and helping my science. And I'd like to share one thought is that you may see that all the presenter have presented lot of chemistry things, and which is you are not able to understand properly now. But believe me or not, the BSc, what I learned in the Calcutta University when I was studying, after that I find with that knowledge we can explain almost all the fundamentals which we are doing in the present science. So I encourage you to read your bachelor very deep and thoroughly. You are lucky to have such young faculties like Dr. Shubhradeep, Dr. Rahul, and Dr. Samasis, who has enormous experience in the field of, enormous experience in the field of research and chemistry. So with this, I thank you all for your patience, and also all the experienced faculties in your college I acknowledge for their teaching to you. Okay, thank you all.
Thank you, Dr. Shamrat Ghosh, for this beautiful presentation and the talk. It was great. And due to the time limit, we are very sorry that we cannot take questions. And I would request all the attendees to, if they have any question, please write to Dr. Samrat in his email ID. Please, if you have any question, talk to him. Now I will request our head of the department, Dr. Ajay Kumar Manna, to present and the closing remark. And so, sir, please go ahead with your closing remark.
Thank you, Subhradeep. Good afternoon to everybody. First, I would like to thank distinguished and honorable speaker of Raman 2021. Dr. Sujit Kumar Ghosh, Professor IJR, Pune, also alumni of Ramananda College. Dr. Dibbyendu Das, Associate Professor, IJR, Kolkata. Dr. Praloy Kanti Shatra, Scientist, Center Nano and Soft Material Science, Bangalore. Dr. Manas Panda, Associate Professor, Jadavpur University, Kolkata. Dr. Anivesh Samanto, Assistant Professor, Srinagar University, Noida. Dr. Shamrat Ghosh, Scientist, CSIR, Central Leather Research Institute, Chennai, for delivering their nice and informative talks and which enrich our audience. Thanks to all the participants, teachers and students, and member of organizing committee, especially convener of this webinar for making it a grand success. I am thankful to our principal ma'am, Dr. Shapna Garai, and Dr. Muhammad Ali Khan, coordinator IQAC, Ramananda College, for encouraging and inspiring and supporting to organize this webinar. In this pandemic situation, the webinar is specially designed for our students who are learning chemistry and material science and technology to inspire and encourage them for research work in future. Besides this, the topic is chosen for its current, which has its high current impact. Nanoscience, nanotechnology, supramolecular chemistry are the model tools for developing the new high performance and smart material for industrial application as well as medicinal application and energy uses. This includes more durable construction of material, therapeutic drug delivery, and higher hydrogen fuel cell that are environmentally friendly. Potential application of carbon nanotubes in their treatment of tumor and cardiovascular disease are getting more and more renewed attention. Nanoelectronic device is a multidisciplinary. Nanoelectronics is a multidisciplinary area composed of quantum physics, device analysis system, and integrated and circuit analysis. Nanobiotechnology, bionanotechnology is applied in the field of nanomedicine. I do not lengthen the list of application of nanoscience and technology. Furthermore, with these few words, I want to conclude this seminar. Again, I give thanks to all the participants and our distinguished speaker. So I think the webinar will end here.
I just have one last announcement regarding thank you for your patience and your participation, and all the participants will get a link for your feedback. Please provide your feedback and also suggestion so that in future we can do better. And with that, I think we will close this webinar. Thank you all.
Thank you.